I can. Yeah. What do you expect? My wife's like, only 3? Yeah, whatever. Yeah, Coffee Compiler Club. It's, December 31st. What do you expect? Oh, here's Bill. Well, there you go. One more. Anything to do with compilers and language runtimes, all fair game. I think everyone here has heard the drill. I reserve the right to moderate. You're going live onto YouTube whenever I get around to it. It's pretty quick these days. No special agenda. Ask what you want. Fire away. That's the end of my spiel. Let me throw Bill onto the I made it list.
Thank you.
Yeah, I don't know what it's good for, but it helps me not spam people who don't want to be on the list anymore. It's what it mostly uses for. So Reddit went hog wild on this. I will throw into the chat. I probably should throw into the doc. Huh?
It's interesting if you keep those lists of attendees. One of my relatives was digging into the family tree and found like this great-great-grandfather attended a Freemasons meeting in 1905.
Ding. There you go. No claiming that, oops, I took somebody's careful formatting of numbers out. I don't even know how to get them back here. That's it. Okay, fine. And it's a long, drawn out thing. And Cameron and Kirk Pepperdine both posted into it because somebody was being foolish. And what did you expect out of a Reddit thread? And they both told me about it. So I went and threw my 2 bits in, but mostly there's already sensible people were beginning to chime in, so it was okay. But it was like, why does functional languages slow? And so this was like a leading question saying, basically flame me now and I'll flame you back. Let's get a trolling going. And sure enough, the trolls showed up. And a little sensibility later, it's sort of.
I mean, there is something to be said for impedance mismatch between languages and CPUs.
Yeah. Exactly. That was the primary theme was impedance mismatch. The functional guys got shit tons more work to do to get to the point where the C compilers start from, and they don't always make it. And that's the performance issue. And that's because CPUs are what they are, and that's because of physics. So I don't know what a better CPU design would look like. There's some theory that says there's some completely radically different CPU design, roughly the same process technology, but radically different layout of transistors to get you something that's like better in some ways.
So there's some chance that that's going to reverse because most of the ways we make computers now basically look like Turing machines.
Yeah.
But quantum mechanics looks a little bit more like lambda calculus. So it is possible when we start getting close to like H bar on things.
Yeah, it's not lambda calculus.
It will reverse, but
I would say it's not lambda calculus, but it's definitely radically different than a Turing machine. Yeah. So yes, maybe. Yeah, maybe. I mean, I think there's a space for radically different technology within the same silicon process with different layouts somehow. And for years there's been the back and forth with like GPU guys and memory as processor guys, bouncing back and forth, and nothing quite stuck. GPUs have stuck as a solid second man. But a processor is a processor, and that's what we have. So fine. So the second theme that came out of that was just basically allocation has bandwidth costs. So I've been pushing on that one for the past 5 or 6 years. Good to see some other people echoing it. And that turns into performance issues for these garbage collect everything or allocate furiously and garbage collect everything languages.
So that means just bandwidth cost means that it is cache misses. What's bandwidth?
Yeah. No, yes and no. So processors have a number of hard limits on resources. One of them is the amount of traffic you can run back and forth between main memory and the processor. That's bandwidth. One of them is the latency to main memory, which is how long. But not how long. It's how long an individual transaction takes. So bandwidth is how fat is the pipe. Latency is how long is the pipe.
Right.
Okay. So cache miss costs you 1,000 operations not executed, 300 clock cycles times 4 ops per, roughly 500 to 1,000 ops didn't execute. That's latency. If the processor is furiously prefetching, the latency drops. Okay, but the pipeline's only so wide. And one CPU on a modern x86 that's common pizza box variety, one CPU can run you out of bandwidth. Two will already max the bandwidth and then have certain share.
Yeah, right. That makes
okay.
sense.
So if you get an 8-core, one socket 8-core machine, and you have 8 cores running, they're dividing the bandwidth like by factors of 4 to 6 of what they actually get.
Right. Yep.
So all the prefetch in the world doesn't matter because they're not actually able to prefetch to keep up. So you're back to full latency plus.
I see.
To go get that cost.
Correct. Yeah.
Okay. So then when you allocate, it's a bump pointer allocation. That's 1 clock cycle. The memory you get is not in your cache and has not been since the last GC cycle. So to touch that memory you just got, that's your 300 clock cycles, assuming that you're only paying latency. If you're out of bandwidth, that's a lot higher.
Oh, I see. Okay. Very interesting. Okay.
Right. So if your theory is garbage collection is cheap, and here's the cheaty bit that messes people up. You know the bump pointer allocation is 1 clock cycle because it's a thread local L1 cache, got the base of the T lab. I bumped it compared to a register. I predicted correctly. It didn't run out. 1 clock, no problem. If I look at my GC cycles and I'm allocating furiously, it's dying furiously or I ran out of memory. So it's actually dying furiously. So it's dying young. So young gen works. Young gen allocations are super cheap. I look at my GC costs. My direct GC costs are very low. You'll have high micros, low nanos for young gen collections on a fairly largish heap. And you're thinking GC costs are super cheap. Once a second, I'm paying 1 milli out of 1 in 1,000 for my young gen collection. What you don't know is you're stalled waiting for memory bandwidth and all those fresh objects at a 100-to-1 ratio, and that's where all your costs go. So GC profiling tells you GC is cheap. Direct CPU profiling and inspection tells you that the bump pointer allocation is cheap. You're endlessly out of bandwidth. You're endlessly missing in cache. You're endlessly flushing your L1, L2 caches out to make space for the new stuff, which is streaming in and evicting good other things, and then streaming right back out because it's dead and the CPU doesn't know it's dead, so he streams it back out dead. So it streams in dead, it's filled with zeros, it streams out dead. It's a big waste of bandwidth in all directions.
Okay, that's a lot. So I kind of ran out of bandwidth, so let me
yeah, okay, fine.
Just to state it. So basically, if I'm using GC, then it seems to be cheap to allocate because that's bump pointer allocation. Maybe that's in the cache. I don't know.
Yeah, it's usually in your cache. The actual pointer is being bumped. Yeah.
And then, but if I'm allocating a lot, then I run out of memory. And so I have to do a GC.
No, it's not if you're allocating a lot. Every time you allocate, the memory that you get from that allocation has not been in your cache since the last GC cycle.
Oh, okay. Hang on. Let me make sure I answer. So when I did a GC cycle,
from the processor's point of view, you did a GC cycle a second ago, an eon ago, a billion instructions ago, 1 second. Right? Okay. At that time, that memory that it's now collecting for that cycle, the last time it was in your cache was the last time a bump pointer passed over it.
Yeah.
So it's the bump pointer streaming through memory.
Yeah.
And then the GC wipes it all and it resets and it streams again. So it's as if you're streaming through a vast array of memory.
Okay. So I don't quite follow that. So basically when I do a GC, what happens to my cache?
So what has happened already is your cache has been continuously flushed by the active allocation.
Right, correct.
When you hit the end of the memory and you do a GC cycle, your cache is what your cache happens to be. GC will screw with it some, it's no big deal. It still contains objects you recently allocated, plus your live working set you're doing shit with.
Yes.
Okay. And now you're dropping out. I'm doing moderator management shit and someone's texting me.
Okay.
Oh, I gotcha. Okay, Cameron says he's coming on, and no. He's enjoying his slopes time. He's about to log in from a hotel room at the ski resort.
Okay, I'm gonna get my coffee since this is Coffee Comparative Club.
Yeah. Okay, so I'm sorry. So say again, where we
Oh,
at?
yeah. So basically you had just done a GC and it didn't bother the cache too much,
Yeah,
but basically
right.
I've been flushing
Okay.
as I allocate a lot of things because eventually I ran out of cache room and
Right.
it reads the next page or whatever.
Okay, so all the things that remained live of that collection,
Yeah.
which was very few of them, young gen collections typically work well. So it shrank down to a small fraction
Yep.
and got moved somewhere
Right.
for the collector. Okay. Now the garbage collector hands you back to the start of where the memory is fresh and clean again.
That makes
Which
sense.
is probably where you allocated last GC cycle. Because it's reusing the same memory. It's just been declared dead, cleaned out fresh, and available now new.
Oh, I see. It moved the young gen. The people that survived young gen are actually somewhere else. And so now we're having a new young gen. Maybe it's the same as the old one.
Yeah, right. Young gen got bumped a
Okay.
generation. It moved to Eden or
That
whatever.
one.
There's a couple people play games here, but you compress the young gen that survives and haul off to the side so that you can hand out big slabs to bump pointer again.
Yeah.
Right. So this is all done for like multiple cores. So everyone has to have a big chunk. So you have a lot of bits. You don't want a lot of fragmentation. So you move objects to reduce fragmentation. Everyone gets big slabs for their thread local allocators.
Yep.
Okay. And you're back allocating basically the same virtual memory that you had before.
Yeah.
But after it has already been wiped out of your cache.
Right. Oh, I see. Yeah. So, but now the first one has to, it's a new place, but if I keep bump, then I like for a while, I'm not, it's in my cache probably.
Well, it's in your cache.
Every time I do a new, it's not in my cache. I think that's what I heard.
Every time you do it's not in your cache. It becomes in your cache. You use it for a while. Yeah. Because the typical behavior is you're done with that object quickly. You know, young gen works because 90% of all allocations die very quickly. Yep. Okay. It's still in your cache physically. You're done with it. The program doesn't understand that you're done with it until a GC cycle runs.
Right.
So lifetime assumes it might yet get used.
Yep.
In practice, statistically, it does not. The processor eventually keeps loading new and new and new into the cache, and the cache, and the cache, the cache is full, has to evict.
Yeah.
He evicts something hasn't been used in a while, which was this thing you allocated one cache sized worth of allocations ago. So 64K cache, you're allocating X bytes a second, some fraction of a second later, this thing hasn't been touched, you throw it.
Right.
So it's a dead object, gets written out. But that's to make room for a new object that comes in.
It's written out to main memory.
Yeah, it's written out to main memory. Yeah, yeah. All the changes you did to it, you modified it, you filled it in with a mark word and a class word and an object installation, all that.
I don't need it anymore, but the GC doesn't. We don't. The runtime doesn't know that yet.
The runtime doesn't know that. Yes, that was the thing I did with Azul's stack-based allocation, was to just exactly avoid that. So Azul did custom hardware for allocation, where it could tell the underlying memory hardware that it did not need the contents of memory. He had a new piece of memory he wanted. He bump point allocated a new piece of memory. He wanted it to be filled with zeros in his L1 cache. He wanted it coherently around the cluster, not in anyone else's cache. Statistically speaking, it would not be in anyone else's cache because the GC didn't have any bugs in it. So when you bump pointer allocated, it was in fact the case that no one else had use for it. So the hardware had to do a handshake to validate that the memory was not in anyone else's cache, or force a flush if it did. And in this case, because you were going to write it, the force flush was to say, Mr. Other cache, throw this away, don't even write it to main memory. So there was a special cache protocol that said, I'm doing a cache line 0 of this cache line and this processor. All the other processors would check to see if they had that cache line. Typically they did not. If they did, they would throw it away.
So this was a no load zeroing of a memory.
Yes, it would zero a cache line without loading. So you didn't eat the bandwidth to load from memory. A new object.
And if I just call calloc, I'm not normally going to get that.
That's correct. The x86 hardware does not have a don't load it from memory, even if I'm going to fucking zero it. There is no special instruction that says don't load, just zero and make it coherent around the cluster. There are special instructions that say my intention is I'm going to write only. My intention is, or whatever, these are hints to the cache to do this or that. But the coherency protocol under the hood still loads it from memory. because as a son and later, looking at it from outside, we desperately tried to get Intel to give us any way to not bother to read these lines of cache that every core was going to read repeatedly and simply zero. And there was
But you better know that you're going to zero the whole cache line.
And we knew that we wanted to tell the hardware we were going to zero the whole cache line. How do we tell the hardware and therefore optimize and don't load from memory? And Intel wouldn't give it to us. There was no way to get it. Maybe these days they do. I don't know. We tried desperately for years, both at Sun and at Azul, to say, please, sir, let us tell you that we'll zero it. Can we do a string zero instruction where it's cache line aligned start and finish? Even one cache line aligned start and finish. What hint can we give you? In the current instruction set that tells you, don't bother. None. Suck. So,
But in Java, the fact that all objects are on the heap, do you think that's a big language design mistake? Because one of the strengths of Go is that you don't have to have everything on the heap.
okay, so you have to be careful here. Where do you have things if not on the heap? There's 2, 3 places that people have different names for. I'm trying to make sure what name you're using. There's registers, which doesn't hold big objects.
Sure. No, I'm
There's
thinking of the stack.
memory, which there's a garbage collected heap. There is a manually managed heap. It's 2 concepts for memory. When you say Go doesn't have everything on the heap, what are you referring to?
What I mean is this, you can allocate objects on the stack, right? I mean,
Yes. Okay. A stack.
just
Those are
like
cool.
in
You're
C,
right, stack.
yeah,
Yes.
C or C++.
Yes. Okay.
You don't have to necessarily put everything on,
So right. So in the land of Java, there is an effort made by the JIT under the hood to put things on the stack called escape analysis. It's only partially effective. If you had
for
a
example, if you allocate an array of objects in Java, you have no way of controlling.
That's correct.
If you wanted your objects to be laid out, sequentially, there's no way to control that, right? Because you have to allocate pointers and then allocate individual objects, and they could be all over anywhere.
That's correct.
In memory, right?
Yeah. Mm-hmm.
Isn't that like a fundamental kind of issue with how Java was designed?
It's not that fundamental. So we go back and forth here a couple different directions of this. So there was definitely a time when I could have made the JIT and the garbage collector understand how to do a 2-dimensional array allocation such that the underlying runtime guaranteed you that all objects were in order, and that therefore, and fixed size, so that therefore you could do array math on objects larger than a primitive, int or float or double or whatever. And that would let you have basically Fortran style 2-dimensional arrays or C style array of structs with direct array access to the contents of the array elements, and drop the headers. And this is what that's what the value types in Java is all about, is exactly to do this kind of behavior. So this can be done in the JIT, and in the runtime, it wasn't. If you do it manually, then you have to do manual memory management, which is what Java's big thesis is, that people suck at manual memory management, and therefore you disallow it by fiat. And the value typing game from the Java side has been taking so long, in part because you have to come up with a way to describe somebody's intentions while not letting them actually do manual memory management, because they'll screw it up. I do manual memory management within the realm of Java all the time by doing object pools. It sucks, but I'm allowed to screw up, and I don't care because I'm allowed to screw up. So statistically speaking, object pooling works in certain contexts, and I do it, and I can be statistically accurate and not be precise. If you're doing this in C land, you must be precise, or you double free and you break your heap and you die.
It is very tempting to have the ability to tag something as this object does not escape this function, and if you can't prove that it doesn't escape this function, then throw me a warning and I'll fix it.
Yeah, right. And I'm
That's
there.
like 2000 thinking. Like that's before we had things like statistics and dynamically generated code.
No, it's not. I claim that this is my intention for AA, is that there's going to be a couple lifetime management variations. And one of them is, I'm going to tell you when the lifetime ends. And if you can't prove it, it's a compiler error, and now fix your code. This is what Rust does, right?
AA is pretty low level though, right?
It doesn't have to be.
AA is the language that Cliff wants.
That's right. But it's no more low level than Java is. Is Java low level? I want it to be low enough level I can write device drivers. I want it to be high enough level that it's as high as Java, but perhaps as high as OCaml or Haskell.
That's kind of
It's still
impossible
lower than
goal.
Java.
I don't believe it's impossible either. And I believe I have the concepts in place and I'm working on implementation.
Yeah, there's only one reason I'd ever tell you it's impossible, which is just to goad you on to do it.
I know. People do that all the time. And occasionally it works. I do shit that everyone says you can't do, actually. And they meant that I couldn't do it. And I did it anyhow. And it was fine.
I think it's impossible to have a high level and a low level thing in the same. I mean, you can do it in a way, but then you end up with a mess like C++.
Okay.
Because it tries to have high level stuff as well as low level stuff.
Right.
So you end up with a language which is just too complicated and too difficult.
C++ was a mess because it didn't have a real goal in mind.
Yeah, right.
I mean, Yarn's a really sharp guy.
Yeah, the problem with C++ is that it worked, so they kept having to add stuff to it.
Right. And then they started.
Languages that fail stay much more elegant.
Yeah, that's true.
So I think trying to do both high level and low level in a language will just make the language.
So your argument here is you'll look like C++, which is a mess. And I claim that's a bogus argument. It's a false argument. I do not have to look like C++. So I'm waiting for another argument that's not. The only example out there is C++, and it sucks. That's not a good.
Sure, I understand. But when you say high level, for example, low level, so the guys who write low level code, they can't stand GC, right?
I understand.
So if you have GC, as soon as you have GC, they're not going to class your language as low level.
I gotcha. Suppose I have an option that says you have a runtime, you have a machine that you're targeting for your code generation. It can be a virtual machine with a garbage collector. It can be raw underlying CPU. So I have a cross-platform where one of the platforms is a virtual machine with a garbage collector and JITting. One of the platforms is a .o file against bare hardware where there's no GC. And if you do allocation, you have to deallocate in a way the compiler can prove it's correct, which is what Rust does. So you have to have a Rust-style allocation. But you could also say, no, I'm targeting a backend that is a runtime with a garbage collector.
So if you think about Rust, Rust tries to be safe with traditional memory allocation, right? And the language is so difficult. So, and if supposing your language has Rust-like features, right, it's going to be as difficult as Rust on the one hand, just because there's no way you could.
No, that's a false argument again. If you use Rust-like features, you pay the Rust-like difficulty.
Yes.
If you use malloc and free in C, you pay the malloc and free difficulty. I claim that that's harder than the Rust difficulty level, but I don't know, maybe.
Only if you want it to be right.
Well, okay, fine.
Well, yes. I mean, this is my personal perception of Rust because I tried to write some simple stuff in it just to learn it.
Right.
And even simple things are not. I mean, try writing a vector in Rust. It's very hard. It's not easy. You have to be literally writing a vector, simple vector, which is simple, right? If you want to write a vector in C++ or C or whatever, it's easy, right? Or in Java.
When you write one,
in Rust,
you don't mean use the standard template library. You mean actually write one manual.
Write one manual.
Yeah. Okay.
Whereas in Rust, it's like it's very difficult.
All right, I have to go.
I mean, it needs somebody to really understand.
I have to go stare harder at what Rust does because my understanding is that one should not be hard. The borrow checker model should not be difficult there. Somebody else do write.
Sounds like a Yorick question to me.
Yeah, I was gonna say writing a vector is not hard at all.
In Rust.
Yeah, no,
I didn't think so. Yeah, so there's some misunderstanding here of what it means to be difficult to write. And maybe it's understanding the borrow checker concept.
So to write a vector in its most basic sense, you need to use the unsafe memory allocation APIs. So that means you import an alloc library and you have like, I don't know, an alloc and a free somewhere and you wrap them in an unsafe block. That's it.
Why does the
Yeah, but then,
checker disallow?
well,
No,
so
where it
my
can
my
get
point is that
difficult.
without unsafe, you can't do it, right?
Yeah, no, that's a fair point. If you have to use unsafe here, then I claim there's a failure in the borrow checker. The vector ought to be written without unsafe. That one seems to be straightforward.
Not at all. The borrow check has nothing to do with this.
Okay.
The way it works in Rust is use of roll pointers by definition is unsafe because it can't sort of peek through. It's just like, oh, it's a pointer. Yeah, you know, here we say it's a pointer to a
Vec
user,
doesn't
but
need to have a raw pointer description though, in its simplest sense.
no. So the basic building blocks of a vector is that internally you have a pointer to some heap allocated thing somewhere. You know, an integer for the number of values and the capacity.
Yeah, I would claim you have an array and 2 ints max of the array length and capacity. Yeah.
Right. And so the way vec is implemented in Rust, it's really just a structure with 3 fields: the roll pointer, the capacity, and the length.
But it's a raw
That roll
pointer,
pointer-
not typed as an array of some kind.
No, so that roll pointer is literally basically void star in C.
I see. Now that would
Um,
require unsafe right there. I get that.
I think it might actually type it as like a pointer. Let me actually look it up real quick.
I'd say, yeah, why can't it be typed as an array?
Well, think about the goal, Cliff.
Well, so Rust
goal is
doesn't
for the
have. You have arrays. There's slices, but they always have fixed length known at compile time. You can have dynamic slices, but you have to heap allocate them, and that's essential. And then you
heap
still can't
allocate
modify
on a
them.
Because the reason is the compiler wants to be able to prove
Fixed
that
memory consumption?
it's not fixed memory consumption. It wants to be able to prove that you're pointing at things that you own and no one else owns.
Right.
And to do that, it has to have constraints on what you can point at. Otherwise, you have to declare it unsafe.
I understand that, but I don't understand, like, this still seems to be doable in the borrow checker notion that I make an array whose extent is known at runtime only. And so I need to have some sort of array notion in the compiler and the runtime that includes the length. So I have a safe version of an array. This is the Java safe array, fine. And a capacity, fine.
That's all a reasonable argument, but Rust is still evolving. So what I'd say is that,
Okay.
you know, the memory model itself
Yeah.
was not memory model per se, but the
Yeah.
borrow concept was not there in the original Rust. I mean, these are things that they've been growing
Really?
from zero. Yeah.
Okay.
So,
But
so I
the-
think
the thing with
there's
the-
a confusion here that the borrow checker is completely unrelated to this. Like basically, the borrow checker essentially only applies when you're using references. And okay, if you're moving, they probably use the same logic. But if I just create a pointer to some heap structure, the borrow checker doesn't do anything with it. It just says, "Oh, this is a roll pointer. Those are marked as unsafe, so you have to put in an unsafe block."
I'm surprised that there's not another option, which is I don't want a raw pointer. I want a pointer to an array.
Right. So it has slices, compile time. You can
It has unknown extent.
unknown extent as
The length is determined at runtime.
yes. Yeah, that's a vec. You can't.
I understand. So the fact I'm saying, how do I do this without using unsafe? How do I make an array? I read an integer from the command line. I want to allocate an array of that size without using.
It doesn't do that. Like
you're right,
slices
right.
need to have a length known.
Okay.
And the alternatives internally, somewhere deep down, you use basically malloc and you wrap that in a safe type like vec.
Right.
So
You're saying you have to go back to malloc.
Rust is like it wants to know at compile time the lifetime of everything that you are referring to, right?
Yeah.
So, for example, I have my I have my Lua compiler. I create AST objects which point to each other, right? I just use pointers. I use a memory allocation pool, and I throw away everything at the end, right? Yeah. Simple, basic stuff. You can't do it in Rust because there's no way to tell the Rust compiler that, look, all this is safe. I'm going to throw away all this memory at the end, because the Rust compiler wants to know at compile time that whatever you're referring to is safe. Right. And it cannot follow that the memory you're allocating is safe because you're going to throw it away all at the end. But the compiler doesn't know that. And the compiler simply won't let you create references through pointers. So there is a very good article. Somebody
Are you
about
referring to something
how-
like a memory arena model where
Yeah.
I like make a space and do a bunch of work there, and then at the
Yeah.
end of painting my frame, I throw the whole thing away? That kind of
Yeah,
thing?
yeah. And in Rust, you can't do that in a simple way. You have to use, there are some library facilities that people have created to do this kind of stuff, but it's all very, very complicated stuff. I'm just saying that my point really was that if you want to make a language which is like low level, like Rust, then it's got to have all these complexities, because then it's got to know at compile time that everything is safe. So, so that you can't avoid the kind of complexity that Rust has because of what Rust is trying to do, right?
No, those are two different arguments. One is that,
Unless you come up with a much better way of doing it, which somehow Rust folks have missed.
right. Well, a lot of folks have missed, but I don't think that that's the need to track handling the vec case and then the arena case separately from borrow checkers and heaps and everything else. The array case is a straightforward lifetime management for a vec. That is, I have an array that has to have a length associated with it to be safely used. The array contents have a lifetime that's managed by the container it's in, the vec. The vec says, I have this array, I need a larger one, I make a new, I copy, I delete the old. I know now that within this code, the lifetime of one of those arrays can be flipped to a different array, but it's not otherwise, seems to me to be not otherwise difficult to manage.
So here's an example. Suppose you have a vector of objects, right, in Rust.
Yeah.
And you take one of these objects and you want to refer to that object somewhere in some other place.
Yeah.
The compiler will want to know at compile time that whatever you're holding a reference to has a smaller lifetime compared to the vector.
Isn't this what
Because
the borrow checker is going to do? As soon as
it's gonna try to make sure that your vector is outliving the reference that you've taken.
Right.
So if you have I was trying something very simple, like an array of objects I pre-allocate,
right,
and I just want to use this as references elsewhere in the code,
right,
and I can't because as soon as the objects go out of they go out of life in the code, the compiler thinks, well, the reference is now leaking or something, and it's going to stop you.
It leaves the vecs. You said vec.get, and you got an object out that now has a lifetime. Oh, so you're claiming that the compiler wants to prove like stack-like lifetime for everything?
Yes.
It wants to prove,
basically RAII with transfer. That's Rust.
It wants to prove that everything, any reference you take is gonna be not outlived by the thing that you took the reference from, right?
Right.
So, I mean, I'm trying to prove that statically at compile time.
Right. So you're saying
very
the vec's lifetime is some execution path that has all the stuff in between that's going to happen. Within this lifetime, the entire vec I called get, and get returned me a value out of the vec's contents. It goes back into this entire lifetime area that has to be underneath the lifetime of the vec proper.
That's right. Yeah.
And if I want to do like a
RAII compiles fine in Rust, right? Like there's no surprises with RAII. So basically, anytime you're stepping outside of what we think of as C++'s RAII model, you're going to get complaints from the compiler if you don't carefully.
I think Rust is great if you're using value types, which value semantics, like you copy objects around. You never have references, then it works fine. Then it's just like C++, no problems. Everything is copied and copy is fine. But the moment you try to get a reference to something, it's a problem. Life is so hard that you will find articles on the web where people they use handles, right? They use handles, integer handles, instead of holding a reference.
Right.
So what you can do is, instead of saying, I will hold a reference to my array element, what you can say is, I will hold a reference to the integer offset of that array element, because then I'm fooling Rust, right? Because I'm telling Rust that don't worry, this is just an int value.
Right, but the
But I know
lifetime,
that is an int value, which is basically telling me,
right, but your lifetime of the object still becomes sub lifetime of the array holding it. And you've just removed the ability to go get the object easily
I
via
have to
and carry
use
it
the,
around.
yeah, I have to use the integer as a proxy, right?
No, I get
Then-
it. But if you say the lifetime of the object is tied to the lifetime of the array, I'm sorry, if you fail to say that, then the lifetime of the object just goes away as soon as you're done putting it in the array. You put in an array, you never look at it again because you get the int offset from the array and you got an index of the array. The lifetime of the object's dead, you throw it away.
Yeah, you basically fool the compiler at
No,
that point.
you fool yourself. You throw the object away, you got no object left. You can't, the index points to an empty content in the array. That's not what you're looking at. So instead, the object lifetime is less than the object lifetime of the array it's holding. And this is why I don't understand why you can't just get a reference to it, because the reference to the object is less than the lifetime of the vector holding it.
You can, provided you can, compiler can prove that
Yeah, right.
at static compile time,
Yes,
that
I
your
get that.
object's lifetime is
Yes, and
within
that's
the
what I thought the borrow
lifetime.
checker was doing. And you're telling me that it's either not doing it or it's difficult to make it do it. And then
No,
I
it's
also see
doing-
people who see, I love Rust and it's easy to use. So I'm done.
Well, I think it is a nice language. It's still evolving.
Yeah, I haven't written any substantial programs in Rust, so I don't know how it feels in the large to try to manage the lifetime. I'm assuming that they had a good answer, but maybe they don't.
Yeah, I mean, I can comment on that. I have like, I don't know, 80,000 lines of code or something.
That beats me by a long shot.
No, so these problems, partially I've experienced the exact same thing. Like Rust, in the way it's implemented, it's not the nicest language when you have basically a compiler where you have a tree structure, and at various points in the tree, you have pointers to the same thing, and they might point back to themselves, basically types in an AST. It's kind of painful for that. You can technically do it with immutable references, assuming that you can make it all immutable. But practically speaking, it doesn't work, because the moment you have one mutable reference to something, Rust says, you can't create another one. I don't necessarily think that's a flaw in Rust. I think it's a byproduct of the sort of type system. As in, if you were to implement it in another language, you'd run into the same problems. If you want to bypass that, you have to basically make it less strict. So that's what I've done with Inco. I took that model and I sort of relaxed certain constraints, with the trade-off that theoretically you may run into some issue at runtime if your code is shit, basically. And that's a trade-off that I felt was worth making, because it makes the sort of compile lifecycle much easier to deal with. So this classic case of, I have an AST and a whole bunch of references, Inco will just support it just fine, provided, of course, that the value you're pointing to doesn't get dropped before the references, because in that case it will create a runtime error and say, your program is broken, go fix it. But that's a trade-off the Rust developers didn't want to make, because that's not really something I think you can do if you run it on some like little shitty embedded device somewhere. Like, you want to know, is my thing gonna run? So it's a trade-off. I think the second issue there is, what I've seen myself is a lot of people, they come from some other language, whatever the language might be, and they try to apply the exact same patterns, and they get frustrated because it doesn't work. And sometimes it doesn't work because it only worked because they were using a garbage collector before. So if you have your classical non-blocking data structures, they're generally pretty doable to implement if you have a garbage collector. And then you do it in Rust, and you just get slapped in the face all the time. But yeah, this case where you have, where it basically gets difficult is recursive, let's say circular types, not recursive. And these sort of typical compiler data structures where you have lots of things pointing to the same thing that might indirectly point back to itself, and you need mutability. Any mutability mixed together, that's where you get handles. That's where I used IDs, which are basically handles, also for other reasons.
Interesting.
But I have to
I mean,
say that
that's what's been
model-
causing the kernel people trouble with Rust is they keep trying to rewrite small pieces of Linux, and it turns out that the kernel is all mutually owned data structures. Everything
right.
points to everything.
And that was what my point was, that if you're trying to make a language, which is like, say you want to make it low level, and you don't want to be in the same bracket as C, then the only other option is what Rust is doing. And what Rust is doing makes life very difficult for the average programmer. Because Rust tries to prove at compile time that all your access is safe. And it tries to guarantee that if your code compiles, then it's safe.
Yeah, right. Yeah. It's a
Yeah.
noble goal.
And yeah, and I think that the way Rust does it is probably the only way you can do it. I can't see how you could do any other way, because when you have self-referential data structures which are pointing to each other, how do you prove at compile time when you can't see what's inside? How do you prove it's safe? It's very difficult, right?
You prove that the WAD is a strongly connected component, and everything in the strongly connected component has identical lifetime. And then you have to have a proof for the things that are pointing into the strongly connected component. This is a straightforward operation for a non-mobile typing. And in the land of mobile typing, where in typing objects are moving constantly, mutating constantly, verifying that you are pointing into the strongly connected component or you're mutating internal to the strongly connected component is the trickier piece. I don't know how to do that one. I know how to manage a strongly connected component as a compile time concept. I don't know how to manage one where it is mutating continuously. And you're trying to separate out folks that are pointing into it from folks that are internal to it. If I make an arena and I'm going to whack the arena at the end, there's one global arena pointer. And at the end, I want to show that all those pointers point back into the arena. No one points out of the arena, and the arena, well, only one guy points into the arena, and that's the arena holder. And at that point, if you whack
Or
it,
at least that all references into the arena are nullable, so that when someone frees the arena, everything else can just become null.
So there's a version that says I'm going to gradually increase the size of, I'm going to incrementally build up. This is what reference counting and the nullable and the linear logic guys do. It's like you nil things, and that nils the next guy, and the next guy, and the next guy. And as long as you have some known set of points in, you can say, I've got them all, I've got the one, usually you got the one, and therefore everyone else goes at the same time. And then there's compile optimizations for ref counting, all that kind of shit goes on. That's a little different than a version that says, I have some collection of pointers that I'm working with in the moment in the middle of a strong connected, they're in an arena, there is some arena that's holding on to the whole wide. And then there's some outgoing edges that are not part of the SEC, that are just terminal leaps. At the end, when I whack the arena, what do I delete? What can I prove? Right? And then one of them answers is that you didn't hang on to anything in the middle of the arena when you whack the arena pointer. But that tells the arena pointer special. So you flag the arena pointer as this has lifetime, and then other people are within it. So I'll prove that you don't have any of those pointers. You have pointers from the arena to other things that will go when the arena goes. That's a performance optimization that says if you whack the arena, I'm also going to chase down all the outgoing leaves and catch them. Right, that's just part of the delete step. Now do this in a typing system. This is what I haven't done. I mean, I don't know how to manage this. Every C compiler, every C guy hacking compiler's done this. Certainly the land of hotspot has a bajillion of these things. Certainly we wrote runtime support utilities to help us manage these things all the time. Prove it at
once you've built that, aren't you a good chunk of your way to just like having a garbage collector?
It's different, and again, different in other ways. So garbage collector says that you are only that you are garbage collecting at any cycle. Arena guy says I'm garbage collecting at a known one fixed point for which I'm willing to exude a fair amount of effort to prove that it's correct at that point. Right. So it's certainly more efficient in the sense I don't have to garbage collect in the middle. It's certainly efficient in the sense that at the time I declare the GC cycle running for the arena, I know I'm done. And so the lifetime management of the arena contents in theory is, zero effort, nuke it all and you're done. Certainly that's how, when I do arenas, that's how it works in practice. At the arena whack point, it's like, it's done.
I mean, that's often what I want at the end of I painted a frame or I served a web request or whatever I want. all that just go away.
Right,
So
right.
from the language design point of view, it would be nice if the language had a knowledge of the fact that you have an arena and these objects belong to it.
Right, right.
Because if you and Rust doesn't have that kind of knowledge.
Yeah.
But if I think a language was designed to be like that, like designed for the fact that you have arena allocators and that the arena owns the objects, and as long as the arena is alive, but you have to be able to prove that. The problem is if you pass around objects, you have to pass around the arena as well, because otherwise, how do you prove that the lifetime of the object has not?
Is there no way in Rust to tag a whole bunch of objects as these all have the same lifetime and will die together?
This has been done in other languages.
Rust has lifetime annotations, so you have to, but it's, I'm not an expert in Rust, but as far as I've tried to use those, but it's not.
I guess
easy.
I will make my question slightly more general. What is lifetime annotation mean to Rust?
So
So
you
the
can
lifetime
tag. Sorry, go on.
I know, yeah. I was gonna say, so lifetimes generally only apply to references, which means even if you have, let's say, 15 references, you give them all the same lifetime. All that tells is these references have the same lifetime. That doesn't say anything about whatever they're pointing to. So as an example, you can create a, let's say a user object, and you create 15 references, you stuff them in a structure. Each reference is one field. You can say, hey, all these references have a lifetime of A. And then Rust will know, oh, they have a lifetime of A. But it won't let it sort of figure out like, hey, this user thing was originally allocated using a region of some sort. So we know it's going to live as long as the region. You basically need somehow to have lifetimes on owned values. And I think if you sort of try to encapsulate this in the type system, you end up with a very complex type system. It kind of reminds me of session typing, where people have tried to type check basically messages as they're being passed between systems.
Java made a bunch of efforts toward small runtime, real-time Java, which had lifetime scoping rules and scoping things.
But so the point is, like with session typing, what you end up with is you define a type, and it's almost like you're defining a full state machine of all the possible transitions. And it also changes sort of how you write the language. So I think with Rust, or really any language, if you in the type system want to say, hey, I have these two owned values, they live as long as each other. I think you end up with a fairly complex type system if you want to have it powerful enough to cover the problems that Rust is facing.
I'm not buying it, but I haven't done it either, so I don't know. It doesn't seem to me. It seems to me there's still a thing that says I have a stack-like lifetime. One of my stack-like lifetimes, it has an arena. Everything in the arena dies, and that stack dies. Recursively below that stack lifetime, I don't have to do any annotations. I call off to library functions with all these objects. The library can say, I don't deal with your lifetime. I'll just manipulate you.
Yeah.
And then
listen to what you're saying, because it's interesting, because you kind of stumbled on a part of the challenge here, which is very few things have natural lifetimes, right? So a stack is used as one of your only cudgels, right? Like plus, you have a stack, and that's the only thing that has a lifetime. Therefore, everything is stack based, right? It's RAII, period.
Well, or it's malloc and free, right? Where if
you're not using RAII, you're an idiot, and you shouldn't be using C++ and go use Python, right? Like that's what I hear from every C++ developer who's who started programming in the last 10 years. But again, it's because you just don't have a lot of things with life cycle, right? And when you don't have a life cycle you can tie to, what do you expect, right?
You get garbage collection, you get a stack. The stack could include, in theory, an arena.
Yeah, so I think garbage collection kind of is a orthogonal cheat in this case.
Oh, it totally is.
Let's discount that one momentarily. And I disagree with Bendu's assumption around garbage collection. Most people who decry garbage collection very good programmers. I don't know how to say it any kinder than that, because, because I would trust Cliff using Java to build something with garbage collection far more than I would trust 99% of the C++ developers I've met who make fun of garbage collection.
No, sure. I don't dispute the usefulness of garbage collection. I'm just saying
I
that
don't just mean useful.
there
I
are
mean-
there are
I mean-
people who want low-level languages. They don't like garbage collectors, right?
Right, but why don't
So
they like it?
it's because it's not deterministic in terms of the
Neither is
so
malloc.
so there
Malloc
this is
is
the
not
reason why, for
deterministic.
example, Go was, that Google's building this new operating system, right? And they initially used Go, and then they rejected Go, and now they're using Rust and C++ and
But
C
Google
because
hires
of
a
the
lot of
fact
people to make
that,
the mistake of reading the internet too. I mean, that's
sorry?
where most, I said Google makes the mistake of hiring a lot of people who read the internet too. And that's where most of these silly ideas come from.
No, I'm just saying that the GC-based languages tend to be not very popular in certain fields, right? That's like if you're
Yeah, it
writing an
depends what
OS,
you're doing.
if
I
you're
worked
writing an
briefly.
operating system, or if you're writing games, for example. For example,
If you're writing a garbage collector, it's really hard to have a garbage collector.
yeah, sure. And also, for example, games developers don't like
Yes, they
languages with
do.
garbage
Yes, they
collection,
do.
right?
Yeah.
Look at the code for Doom. There's a garbage collector in there. He built a garbage collector in C.
I
Yeah, but
see.
that's like 5 people who might be okay. But
No.
if Unity
All
has a
the-
garbage collector, for example, but
Of
it's
course.
All the
from what I've heard,
engineers are
it's
all grabbing GC-based languages for doing the non-graphics intensive.
wait. I was getting there.
Okay, fine.
Well, 1 second. So Unity, for example, I think is probably the only game engine that has garbage collection for sort of everything by default. I think you can turn it off to some degree. But basically any game that is written in Unity, as far as I understand, has a garbage collector running, but not just for the random scripting. It's basically there always.
Wow.
I didn't realize it was there always. Good. Yeah.
Right.
Okay.
I might be
No.
mistaken because they
I
have
should ask
made a
my
bunch of
son.
changes.
He's taking a fucking college course on using Unity.
Right. But so if, for example, if you write in Unreal, the engine itself, I believe, doesn't do any garbage collection. But of course, you can use, I don't know, Lua for your scripting so that, if the player enters some area, you don't have to write the code for that in C++.
Right.
But I would argue that's probably not because it has a garbage collector. It's because these languages are generally fairly easy to write, in part because they have a garbage collector, but not necessarily because of it.
The goal for those languages is not to be super lowest performance, but to be easy.
But there's another interesting aspect that that you're kind of touched on, but kind of we didn't emphasize, which is there's an arena that the garbage collector is in, right? There's a scope for the garbage collector. So the challenge most people have is they think of garbage collection as an all or nothing, like like in the Unity case, right? But if you can segment the garbage collection so that the scope of the garbage collection is like an arena allocator, then it's dramatically more efficient, first of all. And it goes back to what I was saying. I mean, when the only tool you have is a stack, ownership has to be managed by, unwinding the stack. But if you have a Lua, so for example, when in a game engine, you may have 10 different instances of the scripting engine running, right? That means you could have 10 different GCs running, right? But no one of them is the global space of the entire process.
So you're all about having these containers that are nested in a tree. That's your stack. Within each container, you could have a garbage collection or not, according to whatever is going on inside a container.
Right.
But there's still a stack.
That's one way to break it down.
Containers.
A tree, yeah.
Yeah, a tree. Yeah, stack over time is a tree.
I think Nim has the ability where certain pointers are garbage collected, but certain other ones are not.
I was assuming I was going to head down that path. I don't know about Nim, but about the path of some pointers are going to be garbage collected and some are not. Yeah.
And so I think, so similarly D does this too, but they sort of flip around. D has a garbage collector by default, and they're moving a lot of standard library code So changing it such that it doesn't require a garbage collector.
Yeah, right. Yeah, right. As part
But
of
I think
what,
Nim did the other way around, where by default it's essentially manual, and you could say, oh, I want garbage collection here, and I want this there.
it's
Which
definitely
I
in the
think,
zone of your code that you wrote has as part of its type information that it's using a garbage collector or not. And that it runs
so,
in a virtual machine that has to honor the type of the code, which if it needs a GC, then it's piling into whatever garbage collector you're providing in the.
so from what I, sorry, from what I remember in Nim, yeah, you basically in the pointer type, based on the syntax or whatever it was,
Yeah.
it will know, oh, hey, this is a garbage collector pointer.
Yeah.
And I think Rust in the early days had something similar where I think they removed it just before I started using it, but the syntax was something like @GC something, and I don't remember if it was a fully blown trace and garbage collect or some sort of weird hybrid. But there was some form of garbage collection in there.
I think you need an
But it got
annotation that
removed.
says my lifetime is being managed. And now it's being managed by stack, by some enclosing arena thing, by some other typing constraint. One of them will be a GC or whatever, but there's an annotation somewhere that says this is how I manage this lifetime.
And
Yeah,
you know,
can I ask a question about Arena?
Yeah.
Actually here, yes. So is Arena, like I say, I create this concept and it gets allocated somewhere, or just it's a concept. And then when I create memory, it's attached to that one. It could be anywhere. It's not like a chunk of memory that you allocate from.
The
It is
usual
usually a chunk of
story,
memory.
it's a big old chunk of memory.
Big old chunk of memory.
You go to
That's like-
malloc and say, give me a gig or a meg
Yeah.
or whatever your arena
C++
is.
calls a custom allocator. So you
Yeah.
basically get to override new and delete within a portion of the type system.
Yeah.
Okay. And then everything's in that one contiguous block of memory.
Right.
And then when I'm done with it, I say I'm done with it.
Yeah.
Or it's that I'm done with it, and then everything just can be.
And you free once and it frees the whole block. Yeah.
So basically it's garbage. Why are you saying that it's garbage collected kind of? It seems like you're talking about
It's
kind of like-
managed memory.
Yeah.
It is not a tracing collector.
Right.
It does have a generational like effect in that at one hit, you wipe an entire generation out by
There's one
fiat
like-
claiming
they all
that
lie together.
nothing is alive. So therefore there's zero tracing cost. I don't trace it. I don't trace the live things because I fiat, I say it's dead.
Typically, like in a game, for example, you're typically rendering at least 2 frames at a time.
Mhm.
So you're rendering the next frame and the next frame. And then
Yep.
you may have.
Oh,
some-
yeah, of course, yeah.
You may have some residual from the current.
You're
frame.
doing double buffered IO. You're just flipping which arena is being computed for which frame.
Yeah,
Okay.
it's typically kind of triple buffered because you have the one that's being displayed.
Displayed. Yeah. Okay.
The one you're rendering next and the one you're prepping for after
Yeah.
that.
C2 and hotspot does a double buffered effect where I'm allocating IR nodes in one arena and I do a block walk periodically into a new arena. And then I free the old arena and then I periodically block walk them back where the walk just takes all the live nodes and moves them and as a consequence does dead code elimination while it's moving. But it keeps compressing the nodes.
So can I ask one, the other thing that you brought up originally, how we got into this was stack, like putting more things on the stack on the JVM, that was the
Yeah.
question. So what is the cost model? I mean, what is the cost of putting things on the stack? And like, if you put everything on the stack,
Yeah.
there's value semantics, which can be a lot of stuff if you're doing functional
Yeah.
programming.
Yeah.
And it has to be copied and.
Right.
How,
I screwed around with this at lunch at Sun.
yeah,
The usefulness is if you have things that have a short lifetime, you can pick a stack that it will go out of lifetime on statistically. What you want is the allocation for them to hit in your L1 cache or your L2, and then you recycle it and go again with the next allocation in the same cache hierarchy level.
and the cache is like it's the stack is in the cache.
The stack's typically heavy use. Cache holds on things with high frequency use.
Right.
So you want to have new objects that are continually considered new by you, but have the same virtual memory address as the last new object you just made.
Just threw away.
And from the hardware's point of view, you all have the same virtual addresses. So he just caches that virtual address and you're good to go.
So it's kind of like the other thing that would give me that is malloc and free, and I've like got that in my cache and malloc and free. If I can and free it right away when I'm done with it, then I
Yep.
could reuse it.
Malloc and
then-
free totally
why
play
you-
on this. Absolutely. So I did a lot of stack allocation work at Azul for Java objects and was statistically determining their lifetimes without proving that they had this lifetime, just statistics. So I called it
So
escape
what if-
detection instead of escape
wrong?
analysis.
Yeah, and if you're wrong, you box it or something? Or
Yeah,
what?
exactly. You have to, if you're wrong, you have to take it off the stack and move it. Now it's only currently within the one thread on that one thread stack. So you do a thread local GC to find all the pointers to it, which you know are a stack lifetime still because you haven't escaped it yet. So you have a very tiny, very quick, very short GC cycle where you find all those pointers and migrate it to the object's new lifetime. And the new lifetime is either the whole heap for everybody, or maybe it's just further up your stack. In practice, this is strongly normalizing for large Java applications. The lifetime of an allocation site is very quickly determined to be 1, 2, 3 frames up from where it is, 0 through 3 frames, or heap, with the rare occasional guy that's thread local with permanent lifetime. Those happen too, but they're very rare. So once you do the little statistics, then you know the 99%, 99.9% hit rate, you will allocate an object in a lifetime on a stack that will be correctly freed when that stack frame unwinds. It was shockingly good. You know, I got 70 to 80% of all objects in a large JBoss web server under heavy load be stack allocated. The downside was that wasn't good enough to beat the Azul collector. Oh, okay, this guy, I got to talk to this guy. I've been meaning to talk to him for a day here, but I'll move it. Hey, Ron. Yeah, I do want to talk to you.
You're still unmuted
right now with a dozen people. Can I call you back in like an hour or 2 hours? I even have a reminder note to call you back at lunchtime for my time. So an hour, hour and a half from now. Okay, great. Thanks. Bye-bye. Sorry. That's my broker. I do need to talk. It's all good.
Yeah, it seems like most code is going to do best with just a garbage collector and the developer not thinking about the allocation.
I think so, right.
Some things you're going to want to pin down more and say, okay, I need to really have this control.
Yeah.
I worked on one system that literally all memory in the entire system was allocated at compile time. There were
Yep.
only globals. You weren't allowed to use the stack. You weren't allowed to call a function.
Any hard real-time embedded system wants to play those kind of games. Yeah.
Like it was a radar and it needed to read the sensor and it needed to read the sensor at the speed. Because if it read it a little bit faster or a little bit slower, like the whole image would get skewed.
Yeah, real
like,
hard real-time. Yeah, I did those too.
Like you don't have
call
a stack in that. You
Yeah.
just have a state machine.
You don't call malloc in the core hot inner loop of your sensor scanner. Yeah, we had I did the laser printer thing that was you fed a line description to a bit slice computer, one line ahead, and the paper rolled at whatever resolution you got, 1200 DPI. So 1200 times a second, you had to have a lines where the data jammed into this thing. So the guy stuffing the hardware, he did not do any allocation. He read a pre-canned sequence of data that was variable size. The bit slice computer decompressed on the fly and shit, but he read however many bytes, 10 to 1,000 bytes, and jammed them in a hot loop. And he waited for the interrupt, and he did the next one. Fine. All it's saying is you cannot call malloc and free, you cannot call GC, you cannot call allocate in any of these tight timing things.
Right. And even that can be JITted. Like
Yeah.
you could distribute source to something and say, hey, when I start up my printer, I'm going to compile all the code in the JIT and then get to this point where it's like all globals and really locked down. And
Yeah, right. And I would like compile,
still be able to write your whole
typing
printer in
time,
one language.
source code annotations that said, and I promise you I can convert this into hard real time, or I cannot, and then you have to prove something to me about it before I can let you type it.
So on the system you were working on, how did you assert that?
Oh, I
to
did.
make sure-
This was when I was 22 or something, and we eventually put the.
So this was back in the era of like fourth.
Yeah. This was a fourth based system with a lot of 68,000 assembly code. We eventually put an assert in that said assert like behavior that said we blew it on the line length. That we we had to have the line stuffed before the bit slice computer started the line again. And the bit slice computer had an annotation and a hardware that said, I'm done and I'm starting to read the next line. Like he read, and then he was hard real time, really in the silicon level, and he was feeding bits to a transistor that was lasering up and down, turning the laser on and off according to writing the line. And he was reading in the background. So he did two things simultaneously. He was double buffered, and we were the third layer. So we were the triple buffer layer, or whatever you want to call it. So the guy stuffing it in the 68,000 level, he had to be done before the bit slice computer came around and started reading again. And the bit slice computer threw a tag saying, okay, I'm going. And if you weren't done, then when you got to the line, you knew you'd screwed up. But all that meant was the bit slice computer read trash and the line was, garbage. And so you just, saw that after you run enough complicated pages through, you didn't hit that anymore. And when every time it failed, you went back through and it was all deterministic. So you could see what you had produced that you couldn't keep up with the line feed rate. And the answer for us was typically, okay, we're going to degrade the image quality by approximating tiny little line segments with run length encoding that was being de-run length by the hardware into larger, longer segments, but fewer of them. And you lost a tiny bit of resolution in the core piece of this complicated image that you couldn't see by eye anyhow. You need magnifying glass to see these things. Fine. But you had to do it. So there was no compiler assertion. There was a runtime assertion tested that we verified didn't happen. Same runtime testing you get for every continuous integration testing sequence. You didn't see any tests fail at runtime in your testing harness or whatever. Absence of evidence is not evidence of absence, is what I'm trying to say, right? The tests all passed. Great. It's as far as it went. Now, prove that that I could stuff the thing. Well, what we really proved was that we could get away with X many bytes of stuffing before we ran out of time. So before we started the page rolling, we verified that everything we were going to stuff was fewer than ever many thousand bytes. It was actually a rolling window of 3 or 4 lines that had to, probably 2 or 3 lines. That had to be sum total across the rolling lines less than some number, which wasn't more than a couple kilobytes total, 1200 to 2K or something. I don't know, it wasn't very big. Once you proved that, you could stuff the thing in hard real time and keep up. That was what we turned it into. So we added an assertion, but we didn't get a compiler to assert for us that it was stuffable. We instead eventually decided that as long as no sequence of 2 or 3 line vectors are each in some more than 2K worth of bits, we'll be able to keep up. But I don't know how to prove that one. I'm not going to try to. Whereas the lifetime management thing, I would like to be able to prove, like, okay, there's a garbage collector or escape hatch. You can say I'm garbage collected, but I want to have a.
Cliff, how would you solve, out of curiosity, in this context, the Python plugin problem? And by which I refer, most of the time when you want to interoperate from Python, you need to use something like C or C++ or even Fortran, because you couldn't really use Java or C# because they would have rather heavy GC collected runtimes. So what is the best way to have an allocation? I think the allocation pattern for all of Python plugins is basically a super simple subset of RAII, when you never escape anything from the C or C++ plugin, except maybe the final output data that you return to Python. So that should be simple, but I haven't really run across a solution that would be.
You're talking about if I run, I do a foreign function interface to some other code.
Right, like from Python.
He does allocation.
Mm-hmm.
And prove that his lifetime of his allocations is correct when I call from Python to that other thing.
Right, and I would say it's at most once use. So either you return 0 allocations, so either you escape 0 allocations from the plugin code, because maybe you just return one number that is a summary of what you do, or maybe you return one allocation, which is maybe a vector of data that you have transformed.
Okay, we need to refine the problem some more. So I call a foreign function. He immediately rootkits me and wipes my machine out and scribs the disk. Is it the behavior I want? Can I stop it? Can I start it? No, I can't do anything about it. So I call a foreign function, I lost my management. So what management am I guaranteed when I get a return back? So the foreign function immediately allocates all the memory in the universe, and I run out of memory and my hardware crashes and dies. The foreign function immediately runs all the memory in the universe, and the Linux kernel says, boom, killer, bam, you're shot down. I have no control, so I lost it. Okay, so in that context, what can I guarantee out of this thing I just called? Not a whole lot. He promises me he's well behaved. I have to believe him. He's in my trusted computing base now. He says, I have some things that I need, so I'm going to allocate. I go to some other allocator to get that memory. Now, do we run the allocators together and say he's allocating in the same malloc-free heap as the C guy that I'm using is allocating from? That gives me one kind of behavior. So he can run my heap out. He can leak into my objects. He can torture my heap or whatever. He can do things in and out of the type safety of the system to break things if we share a heap. He says he has his own heap. He goes to the OS himself to get memory in a private OS only, his only space for himself, and he manages it himself. That's great. If he runs his own memory out of memory, it's his bug, and I called some trusted thing that was not itself very trustworthy, and he crashed himself.
So pretty much whenever we use FFI, we have to resolve to unsafe in some way. Is what I'm hearing.
Right. So now you can up level the game a little bit and say, I call a guy who's FFI and I want to communicate to him by handing him some of my data, and I want to get data back from him. How do you gate that interface? I'll assume that he's trustable on the other side.
Yeah, the closest thing I saw is, and that's a very different context, it's BPF. So there is a very restricted interface that you can use to write kernel, Linux kernel plugins. And this interface is statically verified in terms of which operations you are allowed to use.
That's,
So
that's pretty different. That's pretty different from a Python FFI.
Yeah, it's as it currently exists. Yeah.
Yeah. So
that's designed to run your interpreted code in ring
So
0.
my thinking is some kind of capability system for the allocators, where you are only handed a subset of specific allocation techniques you are allowed to use.
There's a couple of techniques that people have tried that work with varying degrees. So Elm does copy in, copy out. I hand to JavaScript a raw pile of bits that JavaScript eats and hands me back a raw pile of bits that I eat. And the lifetime management of the raw pile of bits is pick one side or the other. Somebody's responsible for it, but we don't otherwise take anything across the firewall except strongly typed values left or right, because I check them at one. Basically, I serialize and deserialize across the line. And then there's only the management of the buffer that does the serializing, deserializing, but no one ever trusts the other guy, basically.
Right. I mean, the only other approach, you would have to go into full typed linking system. And currently, this is nothing that exists. I mean,
well, there's another option. So Java says, I'll hand you handles. So you can't look at the core guts of an object I hand you, except via operations you can do on the handle. And you have to pay an indirection cost to get at this object every time. And I will validate every operation you do to it, because you're going to call back into the VM with the handle and say, get a field, put a field, and all operations on the object are type safe with this huge overhead. That's another common behavior. And included in here is people where you hand some guy a bunch of objects via handles. He gets a bunch of handles. And then he hangs on to the handles for a while. Then he hands you handles back. So your lifetime of your garbage collector has to be everything that I put in the handle that I handed off to a foreign function is forever, because I don't know when the handle is going to go dead, because the foreign function hangs on to it forever and a day. And then there are people who say, or versions of the version of the Java, which says, I'm done with the handle. You can delete the object now. It's not permanently alive because FFI hangs, or I'm not done with the handle and I never free it because my own self is some kind of long-lived parallel C program, and I'm using this object indefinitely.
Well, the advantage of that model is that it's scale. I mean, that's basically REST. I go to a website, it hands me a UUID for an object. If I want to interact with that object, I make a new request.
Well, right. When I've done this kind of a game before, I usually put a lifetime, that's a time, a number, a date on that UUID. Here's a UUID. It's good for 5 minutes or 5 hours or 5 days, but then, it's gone. And then there's a finite cap of them, and then I don't have the resource limitation problem. You run out of holding on to them. I handle 1 million requests a second, I hand out 1 million UUIDs a second. I hang on to the UUIDs and what they refer to every time. well, I'm picking up 5 million, times size of request per second. I'll run out of memory for long. You got to have a
Yeah, an expiration date's nice on that.
You have an expiration date on, yeah. And the Java handle model does not. I think the expiration is explicitly. You said you got rid of it. Or, the usual one is that you don't get to keep it past the handle. Like the handle is explicitly denied you. The problem, of course, is that the other side cheated through the handle anyhow because he didn't have the overhead, and he cheated and looked at the object, and then he cheated and scribbled on it, and you moved the object because you thought the handle was done, and so the FFI guy tortured your heap, thinking he was all doing good stuff, and in fact, he scribbled on random space, and things broke. Java went round and around on what a good FFI interface was or is for a long time. And eventually we had to make people move to a rule that said, you can't look through the handle or else all bets are off. You're not trustable. If you peek through the handle in any way, you're not trustable. If you want to do an operation on the handle guy, you must call back and we'll do that. Furthermore, the lifetime of the handle is typically stack. And at the first call, and if you call in and out of the VM, that's good. But when you unwind that call, handle's gone. If you hung on to it, it's dead. And it's not allowed to be tortured anymore. And we marked the handle so that if you called back with an invalid handle, we told you that you had a dead one. So there was a bunch of safety things put in, but they're all, you volunteered into it. You could be unsafe on the FFI side and peek through a handle that had been turned off and disabled and whatever. And people did for a long time until they got tired of their code breaking.
So with all this background, what are you thinking for FFI and AA?
I'm going to do something similar in terms of a best effort. I am going to say, if I FFI call, the FFI thing goes into your trusted computing base. And that is part of the type. So if I look at a module and he's called off to some BLAS vector, the module description will include, and I use BLAS as part of my trusted computing base. So if you want to call me, you're trusting BLAS as well. Or you're trusting PGP for security or whatever, right?
So you're just going to get something that's like, hey, you call me, and by the way, I call DirectX because I put pixels on the screen.
I call DirectX. It's in your
You
trusted
call
computing
me?
base.
Blink.
Right. Which means you can have a type annotation that says, and I do not trust, specific things, or do not trust the following, or I want to be, trustable, so I'm not disallowing, like, I don't add anything.
So when you say type annotation, that's something where you say, hey, here's a particular piece of data, but by the way, this piece of data is not for DirectX. If you never hand this to something that might hand it to
that
should work.
Yeah, I didn't think about it that way, but yeah, that should be the right thing.
Because there's definitely pieces of data that I want to tag as don't put this on the screen or don't send this across the network.
Right. So this anything to do with another one is raw strings that I'm going to interpret as execution commands. This is the SQL injection attacks and shit like that, or personal information that I didn't want to escape as unhashed or something. Yeah, the theory here is that there's a scope, stack-like scope, tree-like scope for annotations that include FFI, whatever what you're going to expose to the data that's here. And then there's another set of annotations that says I shall not, like, I don't want, this code should never accidentally add anything to the trusted computing base. It shall be in AA only. Right. And so I can publish a module or a library routine that everyone can trust because it has nothing in its trusted computing except AA. Right. Conversely, as you said, hey, I'm going to be a Unity guy. I've written in AA. I'm going to grab DirectX. Great. Everything that you hand me probably leaks into DirectX, so don't hand me shit. Right? And the typing system can help you validate that says never unknown FFI and I'm a DirectX, and then that's a direct type conflict, and the typer will blow you out and say nope.
Right. So main gets an object that has access to, say, the file system in the network, and if you don't hand a module the file system in the network, it doesn't write to the file system.
It can't write to the file system in the network. Yeah, exactly. That's the current theory where I'm headed for. Having said that, it's not there. I'm just sorting out.
It seemed like earlier you were imagining sys as kind of a global.
No, it would be. You have to make it convenient. So the defaults are, hey, I touched the file system. That's the default. You can say, no, I don't touch the file system. But by default, you can do sys.print and get printf debugging. That's the default. That's my opinion of what the default should be. If I want to know that I'm calling somebody who doesn't ever call sys.print, I'll go ask his annotation for that module I'm calling. Hey, do you call, I say, this is an acceptable set of FFI. He says, this is the FFI I'm using. The compiler type checks you and says, pass or fail. So if I want to know I'm not calling sys.print, I can say that. And then it'll say, no, you can't link against this other guy because he calls sys.print. Main by default will call sys.print. You can turn that off. You can say, and I don't.
And like the rest of your types, most of the time that is inferred. But if I make an assertion that says, this thing does not touch the network, then I can't link against something that does.
Right. Well, the network will come from basically importing sys.io or io.blah, blah, blah, or network.something. There'll be something you say that says I'm doing networky things, and something you say that says I'm doing fileworky things. Only sys.print will be standard.
Yeah, at the very least, it's convenient to give people a sys.net.udp, sys.net.tcp.
Yeah, right. There'll be some things you'll get pretty easily that you can turn off, and there's some things that you want to turn that you can say I shall not accept in a valid link. But the defaults will be, I want to be able to say sys.print for debugging easily. But maybe somebody else says, no, you can't call sys.print because that touches standard out, and I don't want to have logging to standard out or whatever. So, okay, you can turn that off, and then everyone who's sys.print by default will fail the link. And then, you get to the point where the guy was talking about with Rust libraries, where you hack the library to make it less and less dependent upon other features, right? If I have a library routine that does Boyer-Moore string searching, I don't know, something really stupid, I can easily say it doesn't call sys.print, right? It doesn't include #sys.
But hopefully you wouldn't have to say that explicitly. You can just learn it by looking at
well, right. So there's an implicit thing that I can look and say it's not. And then that would just
assuming it doesn't call eval or something that
totally right. It doesn't call eval is a big one. Eval won't be on by default, but if you call eval, then somebody else can say, and I don't want you to call eval. I think that's fair. I don't want my PGP library calling eval.
Does that help if somebody wants deterministic behavior out of something?
There's a couple things that come out of deterministic behavior. If you're single-threaded, if you're multi-threaded, you're typically not deterministic unless you have very strong handshakes between each other. Very strong handshakes. If you're single-threaded, you can be somewhat deterministic. And then there are a bunch of things that break that you don't typically think about. You give me a heap size that varies at the start. I say I'm deterministic. I'm running the same way every way. At startup, I get memory according to the available, a fraction of the total memory available in the box, which varies moment to moment because other processes are running. So my heap size is different when I start up, which means the address layout is different, which means your default hash codes are different, and your reprobed rates and your hash tables and all that shit are all different. So you want to be deterministic? Amongst the things that has to happen typically is I get a fixed size heap if I'm going to do garbage collection. I get a fixed size heap if I'm going to take a hash table from your address. There's a couple other places where,
those seem like acceptable restrictions if you're trying to do the synchronized virtual machine thing where you're like, I've got 7 machines and they each make a fixed log. We are going to apply these transactions in this order so that we always have the same state.
Thing. Yeah. So there's a really nice performance work paper. Basically, a prof and a student were disagreeing on the performance of a particular optimization. And it came down to when it was run in the prof's directory, the directory name included the prof's username and the student's name was different. It's Dubinsky versus Click. And it shoved the hot loop to span a page boundary that was a TLB boundary as well as a page boundary. And the x86 was faster or slower by a large fraction based on the hot loop, was failing to prefetch across a TLB boundary in the iCache. So this turned into them, once they sorted it out, which apparently took some months, to doing all kinds of performance work on environmental effects. And the typical story they found was that environmental effects for running a hot, simple program, tiny, simple hot loop program will give you plus or minus 30%. So big numbers.
I've certainly seen structs where you add a dead byte into your struct, and now it's a multiple of 64 bytes. Totally change things.
Yeah. One of them can be, I went from 64 to 65 and I had fragmentation issues. One of them can be, I went to 64 to 65 and I got ping pong sorted out and I fixed direct cache line conflicts for unrelated fields. This was a case where the stack was taller or shorter by the environment name of the local directory, which included the usernames. And then the stack was being used to access some piece of the hot code, and it spanned a TLB boundary, and they failed to prefetch correctly or something. It was endlessly screwing up there. Oh, the code got laid out differently. How did they had some, whatever, your code got laid out differently for these guys. But anyhow, the point being is that people sweat bullets and compilers for 5%. Environmental effects are way the hell bigger. And what the hell are you worried about 5% here or there? Fix your environmental effects first. And that includes the garbage collector landed you objects that were beneficial or not. Compile time for JITs are a big one. Compile plan for JITs are a big one.
I was going to say, is your ahead of time going to be able to deal with those environmental effects, or do you have to have a JIT to go after them?
No, you could have a ahead of time do it, but the first thing it does at startup is to fix them. Like you want to ask something on the OS is refusing to give you proper things that you need for performance work. So you have to arrange for them outside of the OS, but you inspect the world and promptly do things like layout. And Matt put the paper in the chat there. So that's the paper I'm talking about. Yeah, it's a fun short read. There's another companion paper floating around. I have to go find it. That was another one of these where we did all the obvious things and the answers were all stupid and blatantly broken. And we discovered there was some unrelated, like, fuck it, what the hell going on here thing. And then I still see, even today in my YouTube feed, I get this guy, a Microsoft ex-engineer who did a bunch of core shit at Microsoft, doing performance testing of small functions, the DB language shootout kind of shit, where he's looking at 3% between Java versus C code and declaring one the winner or the other on 3%. I would claim that's well within statistical error, no significant difference. You should draw no conclusion from that. And your testing criteria or your testing strategy lets you totally fall into the camp of plus or minus 30% for stupid environmental effects. And so even senior guys today are still falling into this trap. Yeah.
I mean, performance is hard to measure.
Yeah. Everyone thinks they know the answer. It's easy, right? I write a for loop a million times. I time it. Get a random number back. Good luck.
I mean, sometimes there's good performance measurements. There's a few things that Google tweaked, and it's like suddenly we went from needing 10,000 servers to be able to do this to 950, and you're like, what?
There's
what would you wish going back to this language design question, what would you wish in a language if you were designing it? Like,
that's what I'm doing now.
Yeah, I know. You're obviously trying to probably solve everything.
Yeah, I'm solving too much shit at once. You're correct on that front.
I personally would. I can state what I would wish. I'd probably wish for a language which is small, not very big.
It goes with small.
Probably, and one of the reasons why Java and C have been so successful is because they were small when they started off. So a language which is small maybe, and then maybe have less features, like, for example, don't have multi-threading at all. Make the language like mini VM per thread. Like each thread's got its own VM and own GC, and you always serialize when you talk to another thread, right? So internally within a thread, you never have locking or any of that kind of stuff. So your GC becomes very, very efficient and simple.
So slow down. So this is all you're hammering again and again in sort of the same good points. There's some good points there. Cameron is very much in this zone. This is very much his ecstasy project, where individual computational elements are single threaded. They talk through message passing. It's all optimizable in the hood. The jet can go to town within a core thing. Everything you said there, garbage collector, fast, easy, single threaded, You immediately throw away one of the big common use cases in the world, which is a shared common hash table supporting multiple threads on a big server where they're caching database request lookups and HTTP request lookups. And you want to have a large shared cache structure, large shared concurrent hash structures. And Cameron made his living off of coherence. It was a large shared concurrent hash table, basically. You know, so how do you write a large shared hash table? The reason you write it is because it's hugely more efficient than doing something else. How do you write such a thing into this model? Well, the answer is you don't, because you can't do multi-threading. Like if everyone has to sort through the one hash table thread, you immediately become bottlenecked by how fast one core can hand out hash requests. But the typical story for these hash requests is that they're 99% the same as a fucking hash table. It's correct. I mean, sorry, fucking cache. And it's a cache, it's caching correctly. It's working fine. Because it's caching correctly, it's got a huge hit rate. So you want to have all the threads in the world come in and discover that they're going to get a hit and then go away. And you can totally do this with all kind of concurrent hash tables. But when somebody misses and they have to write to the hash table, you have to have a concurrent, safe, multi-reader, single writer minimum. And there's a bunch of ways to do this. And non-blocking hash map is my multi-reader, multi-writer way to do it. But none of these guys, they start with the assumption there's multiple threads. And there's multiple people accessing the shared data.
Yeah, but shared data causes all kinds of problems, right? So I think the problem is that
it does, and it's hugely more efficient. And
it's more efficient, but it causes so much grief, right?
Yeah,
I mean, so many bugs
I've lived with
systems.
Shared data structures all my life, and for me, they have a known set of problems and a known set of reasonable techniques to work around them, and they're workable. And I wish the fuck I had better language support to work them.
But what would how can you get shared data when you have multiple processes anyway, right? So you've got to have, so you've got to live without shared data anyway. That's my argument.
No.
That's my argument, because
I hear you, but I know that's wrong because I've done it personally. What the hell? I run companies where that was not the norm. The norm was you shared fucking data and you fucking needed to. That was the main product benefit.
Agreed, but what I'm trying to say is that, you know, in order to get high, what do you call it, resilience, you've got to have redundancy, right? So that means you've got to have multiple processes running which don't share memory, right?
Okay.
And therefore, they've got to be on different hardware, maybe in different data centers.
So you're mixing a lot of things here all at once.
I'm just saying that sharing data, there's going to be a point where you can't share data, right?
So
through a shared hash map or whatever, you can't do that.
Okay, hang on. There's a bunch of things you're blending and you're skipping over like big pieces. Single node shared hash table is itself a useful price performance point, where performance is a feature. Single node is super easy to manage and maintain and deal with, and having performance out of a single node lets you skip all the cluster cloud-based coherency shit, and typically gets you 10 to 100x before the cluster catches up, because the overheads of adding a cluster for one node versus one node are so high. So there's a large model, a large performance model, large region of people whose load factors say single node, but multi-core. And that covers this big swath of ground. Then there is, okay, I had to go big because I needed a lot of data. And separately, I had to go big because I wanted redundancy. So the redundancy argument you have to tackle a different way. And that is, what is the mean time to failure between nodes in my cluster? And when do I need more nodes to get me more resiliency? The answer comes back is almost surely software fails first. More nodes cause more failures. And you'd rather, for resiliency, be one node because it's fucking reliable and stable. I sit my one web server on my desktop next to me. It has a mean time between failure of years. So that is the time which my website goes down, years. Right?
If your operation is restartable.
No, the fucking laptop will work until the power's out, and will work through the power being out as well, and the power comes back and it's no restarting. Now, it also can restart, and that's a separate thing, and it restarts in seconds, and it comes back up and the web server is up again. And you know,
Right, but your web server is not going to miss an absolutely critical transaction.
I'm not attempting to go there, but it would write to disk. I've done this where I wrote to disk at whatever snapshot rate I wanted to write to disk, whatever the damn file system would handle. And that was the rate at which you lost a transaction if it came in and then you took the power fail before you got to the disk. And then just treated as you didn't actually get that transaction in. You started the transaction, it got to touch to disk already, and then it completed when you came back up. Yeah, that I've done. So I'm just saying, single node, go there first. As soon as you have to have multi-nodes for resiliency, you're probably screwed in other ways anyhow, but people do that and they want to have enough nines. You have to have a bunch of nines after that. You know, it's not 99. I'm already at 99 with one node. I'm at 99 with 999 with one node. If I want to get more than that, then I need to strip data centers, continents, all kinds of shit. Well, you can get to 5 nines and now you need a cluster. Okay, so that's one aspect of resiliency. Don't go to the place of talking resiliency with clustered, I'm sorry, mean time to failure with clusters. Talk mean time to failure separately. Sometimes you need multiple nodes. You have to be a pretty hard high 9 count before you need multi-nodes. Then there's capacity. Easy to run one node out of capacity. And now your question becomes, do I need to have, well, I have multiple nodes for capacity? What is the failure rate? Well, now you get a multiplicative problem. And as soon as you have a 100-node cluster, because you have capacity, you can have failures. So I did a big data company. We were doing big data math, you know, machine learning at scale. And the answer was, if you weren't trying to be a database, you didn't need any of that resiliency shit. You could get 100 nodes and they'd run for days before you actually have a failure. But no, failure was measured in days, not in years. So you get a 100-node cluster, that's times however many gigs per node, you got terabytes of data, you ran at the speed of memory for terabytes of data. It's fucking faster than hell, but it didn't need to have yet redundancy between nodes. If you're doing what Cameron did, which is coherence, your multi-node caching database, now you need resiliency, and now you need redundancy, and now you need to have copies of the data spread about so that you could not lose when one node went down, and there's a market for that. But don't like conflate all of these markets and all these behaviors together, because they're different for different things. So do I want to have multi-core? Absolutely. Do I want to support multi-nodes in a cluster? Yeah, but that'll be an add-on like thing. That's like a module add, not a language yet. Cameron's in a different zone. He wants to say, I want my runtime to immediately span multiple nodes in a cluster, because he's coming from the multi-node cluster background and he understands that's a useful place to be in. This is what microservices were trying to do, except microservices have all kinds of other overheads that are ludicrous. And that turns into performance as a problem, as a feature. And hey, I'm going to solve my performance with microservices. Well, no. First thing you did when you said microservices is you divide by 100 your performance. Add 100 nodes, you caught back up to what your one node, but you added a huge complexity. What the fuck? Back off and try again. So there are people who want to go there. I claim that's not necessarily a language feature. Cameron's exploring that language feature space. I'll let him do it. I'm not intending to explore the cluster as a language feature.
Hey, what you said, one thing you just said like 20 minutes ago was you wish there was better language support for the concurrent stuff. Is that just a CAS? Because I've heard you say CAS.
Oh yeah, it has to be a CAS. I'm totally gonna have a CAS as a low level, easy to write, one-off thing. Yeah.
Which is for any, I mean, I guess I've been wondering what, because you can make an atomic in Java, and that's has a method that does it, but you want to do it. I mean, what do you want? What is missing?
Right. So I lived before Java had any of the atomic things. When they started bringing up the atomic things, they immediately added a layer of indirection. You're only using a CAS because you have some performance problem that you can only solve with multi-cores. So the CAS is guaranteed in your hot inner loop. Adding an indirection to the CAS and the hot inner loop is like directly in the wrong direction. If it wasn't a hot inner loop, I didn't care about the indirection, fuck it. But always these things are in hot inner loops, and that's the reason.
What's the indirection? It's like go to atomic, and then inside that there's the thing that I'm actually.
Yeah. So I want to have my C++ struct, my Java struct. These are all the same concepts. And the string implementation, pile of bits in memory that's strongly typed to the bits. And I want to go to a field inside of it, CAS that field directly. without any extra bits. So in unsafe, I come along and say, give me the field offset, make a function that says, given a base object and the magical field number, do a CAS there. If I go to atomic field updater, I get an extra indirection.
That makes sense. Why does it have to be unsafe?
Because that was what you could get for a long time.
Oh, in Java, it's
These days you can do it without atomic field updater overheads and without unsafe. And I think you have to go to like method handles or something. There's some stupid else way to do that now.
Okay, but it's not inherently unsafe. It was just on the JVM.
Oh yes, nothing inherently unsafe here. It's just CAS in particular is just a read, modify, write that happens to be atomic. There's nothing unsafe about it.
Any var is what Scala would call it. You'd want to be able to CAS it, and that's it.
Yeah, right. There's, like I said, there's nothing unsafe about it. So there's no language implementation issue there that matters. Now, volatile and atomics in C++ have very special semantic meaning for concurrency that I think I want to honor some technique like that going around. They basically say there is a limit to what the language will allow reordering across these boundaries. And that in turn dictates something to the JIT. And what it means to the JIT varies by whether you're an x86 or an ARM chip, but it means something to the JIT.
So is volatile and what?
Well, atomic for C++. Volatile in C++ means jack shit, means almost nothing. It means you'll get a load instruction in the hardware, but the hardware is free to fucking reorder the hell out of it. So it didn't actually change anything.
That's what it is. I see.
Yeah, for direct memory modifying of memory mapped hardware, the volatile means something. For concurrent shared memory machines, volatile means basically nothing. So if you wanted to have a hotspot JVM written in C++ code and you needed to have multiple threads doing interesting behaviors across threads, you couldn't do it by using the volatile keyword. You had to mimic your own, which we did with macros that turned into pound include assembly language of the correct version of a fucking fence instruction.
So what's your CAS look like? In
volatile gave you a read barrier, no? A write barrier.
Volatile, depending whether it's a read or write, gives you a happens before block, which typically turns into some kind of a read barrier, which varies by hardware as to what that barrier looks like. Most of an x86 is a very strongly ordered model, and it means nothing. It has no hardware to get you the correct barrier semantics. The load versus store typically does need a barrier, but store, load, and load store or store load do not need that barrier.
However, volatile was never really correct for C++. Like even in the 1990s when atomics didn't exist, it was still wrong to use it, and it could be optimized in a way that would defeat the double checked locking pattern was, for example, incorrect. It was implemented with the volatile.
Right. Certainly in the land of hotspot, we quickly discovered that C++ on different, we ported to like a dozen different machines. Wildly varying semantics by different compilers, highly unreliable, and even if the compiler put an instruction there, it didn't do any fencing. So
it basically means
reordered.
It basically means access outside of the abstract machine. So C++ standard defines a so-called abstract machine, which could be thought of a little bit like a JVM in theory, but not quite because there is no runtime.
Very
volatile. And the memory object model in C++, what does it mean to load, what does it mean to store, how do load and store are ordered, is defined in terms of the memory access on that abstract machine. So for example, you cannot optimize some of the load or load store operations. Volatile only tells you that this access is outside of the realm of the abstract machine. So it perfectly matches the embedded application when you may be accessing some port, and maybe this IO port is memory mapped, and if you access that particular address, then you are accessing the IO port. But that's it. It doesn't mean anything about happens before or concurrency or synchronization or atomicity even.
Right. All right. Somebody had another question that got started. Bill, you were asking.
Yeah, probably. Oh yeah, what did it look like in AA, or did you do that yet? Because you were talking about L values.
Oh no, I don't have a syntax for it. It's an unusual enough operation. I'll put it somewhere easy to get to, but not necessarily have any special syntax. I'll give you a hard guarantee that what looks like a function call inlines down to a CAS instruction on the local hardware implementation. I probably will have versions that have different fencing for the CAS. I certainly had a no fence CAS at Azul, and I definitely had a use case for it, which was high performance perf counters.
Actually, I was gonna ask about fencing too, because like, if I have like on the JVM, it's not safely published, it's mutable, but I want to say, flush it, and then I'm gonna kind of never mutate it again. How do I do? I mean, that's possible, right? Somehow? Okay.
It's also possible to flush mutable objects in the JVM correctly. It's certainly a thing I do all the time. There's the JVM memory model I like. And the memory model says there's this notion of happens before. This happened before that. And happens before within a single thread has the obvious thing. It happens for across threads, goes at locking and volatile points. And at publishing of new values. So
what do you say in Java to flush a mutable object?
You do a volatile write. So I have I declare this object to be sorry, I have an object, I have a field which I want to store this, I pointed this object into.
Yes.
That field needs to be declared volatile.
Oh, well then anytime I change it, it goes like as I'm building it.
No, you change it freely. The JIT does what the JIT does on the single thread. It hasn't been published yet.
Oh.
When you write it to the volatile, the guarantee you get is all the stores you have done prior to that volatile write will be visible to other cores if they first read from that volatile. So the guarantee you get in all these languages is very weak, and it's relative the way Einstein thinks about space and time is relative. It's all the observer, what it means. So you cannot say there's a total order and this happened for that in general. All I can say is, here is a point in memory that has been named as a variable.
Yep.
Some guy writes to it with a volatile write. Some guy reads from it from a volatile read. That's the ordering. Things that happen before that write are visible to the guy who reads afterwards.
Right.
That's good enough to build all your concurrent data structures, but a lot of people get confused at Divyundu saying, yeah, it is confusing, or it's not intuitive until you've lived with it for a while. After a while, it becomes pretty easy to sort on what it means. Or at least I found it wasn't too hard after a bit. In the beginning, it definitely, of course, I guess I lived in the concurrent realm when everyone had random, who knows what the hell happened.
No, I think what I was trying to say is that concurrent programming is difficult, and a lot of bugs in the system can be
help me write it. Yeah, I heard you.
I mean, not everybody is going to be of your caliber, right? So you have got to account for the fact that average programmer is going to make lots of mistakes when writing concurrent code.
Okay, so I have an answer for that. I think it's fairly straightforward. Okay, it's a similar answer to what Java was doing with concurrency, at least, which is to say, we'll do all the easy stuff, and the easiest thing is you didn't write any concurrent code. So the Cameron's model is users never write concurrent code. There's nothing concurrent thinking in any of their thinking. They're only writing single-threaded code. And
that is something I think which is I'm also supporting, in the sense that I think that leads to more robust code for the average programmer, right?
I get it.
Not everybody is going to be a genius.
It's the separate question here, which is to say, if you don't trust yourself to write concurrent code, don't write it. You can go be a Java programmer for your entire life, high paid, well, good developer, blah, 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 not write concurrent code ever. You don't need to. If you want to write low-level concurrent libraries that other people build on, you need to be a concurrent programmer. If you want to go use JDK 1.5 level concurrency utilities, you do not need to be a concurrent programmer, except in the very abstract sense. You have to say new thread. You have to understand that you have things running in parallel. Your web server wants to be running in parallel. This is all great. You're not actually writing concurrent code. You might write some blocks. As the worst case scenario, you had to say concurrent hash map instead of normal hash map. That was the limit of your concurrent programming. This is what the JDK gave you, is library routines for doing these concurrent things. I think that's a good point. As a concurrent library developer, I want more compiler support. So I'm saying I want to target myself as a concurrent library writer and give myself some more support. I'm not going to deny somebody else to ever the right to not write concurrent code. You're saying concurrent code's hard, don't do it. Okay, don't do it. But that has nothing to do with AA saying, I enable you to write concurrent code. That has you saying, I'm not going to choose to write concurrent code.
No. So I was not. So I agree with what you're saying there. But when you implement the language and it supports concurrency in the way Java does, it will introduce a lot of problems.
If you never
right?
say new thread in Java, what extra complexity did you see?
For example, let's take a simple example. GC is far more complex to implement in a concurrent world.
Having
right?
implemented them in a concurrent world, I totally understand what it takes to implement a concurrent GC.
So exactly.
So
it's quite difficult, right? You wouldn't disagree with that. It's not something that.
Yeah. But I'm not saying if you are intending to be a programmer to write a GC, you probably better fucking understand concurrency pretty well.
But if you wrote GC for a single threaded VM, it's far more simpler, right?
Yeah.
Do you agree with that?
Yeah.
So it's just an example of the complexity.
That has nothing to do with saying the language supports concurrency or not, making the language complicated. If I removed all the concurrency support out of the language and you're writing a garbage collector for a single thread in the same language, and then I put all the support back in, you won't be able to tell the difference.
Sure. But what happens with Java is that because it makes it so easy to create threads and do stuff, people just do it, right?
That's a slippery
people just do it all the time.
People are given a chance to pick up a gun to shoot themselves in the foot, so they will. So I shouldn't let them have a gun, because if they let them have a gun, they'll shoot themselves in the foot. And I don't buy that argument. That's the argument that says people are stupid and they don't know it. And I'm like, yeah, I'm going to let you be smart or not, and you can hang yourself or not, but
I mean,
I'm not going to say
yes and no. I approve of calling the direct pointer manipulation library unsafe.
Yeah. Okay.
I think that is a better name than direct pointer manipulation library.
Fair enough. So that turns into hide the new thread accessor somewhere just a little bit, right? You have to say new thread or sys.thread or parallel dot yada yada before you got unconstrained parallelism. I definitely want to have array.map, like do parallel array map behaviors under the hood behind your back.
Go has tried to solve this by saying that you can't use threads at all, but what you can do is you can use channels, right?
Right.
Which are like queues.
This is what Cameron's
in-memory queues between.
This is Cameron's solution as well.
Yeah, so you can use in-memory queues, right? Which are efficient and which you can use to transport from one thread to another.
Right.
And you don't use locking, you don't use threads, explicit threads, and your code is single-threaded, right?
Right, up until you do weird shit with your channels that cause cycles and whatever, and the queue's behaviors badly, and you still don't get a good fast shared memory cache. We'll do a single thread cache, and that's like an order of magnitude slower than a multi-threaded shared memory cache. Fine, and you can't implement that in Go, but you can implement Go using some lower level thing. So there is a point that says this is a line I haven't drawn in my own head. At what point do I say AA is able to implement itself? This is what C can implement itself, including all the parallel concurrent whatever behaviors. So I would love to have AA be able to implement itself, including the runtime for an AA that wants to do garbage collection and shit like that. And at some point, you have to bail out and do something lower level than the language supports. And I've already wrapped my head around. I want to do like typed assembly language for AA as a escape hatch, but that's still run outside the model. And then as soon as you run outside the model, you have to declare yourself in your own.
What does typed assembly language mean in this context?
Oh, it just means I can write assembly code to get special instructions, but they're typed in the sense that I understand what you're doing with pointers. So you can't cheat and do things with pointers in assembly that hide them in a way that I don't understand. Up until you declare that I am
unless I say unsafe.
Right, unless I say unsafe. And then in which case, I'm going to say you're using unsafe, and that's part of your type description. And then, at some point I'll say some of the core routines I've used to self-build AA are unsafe, and that's part of the trusted computing base in AA. And that's, you took the C runtime. Where did the C runtime come from? Is that trustable? The things that happened before main, right? was a lot of shit happens before main. Well, a lot of that's assembly and sets up.
I mean,
for
if you
OS
cannot
call.
take the C runtime, that's nice. I find that libc is one of the things that limits portability of binaries that I make.
Well, Java tries to make it more portable by giving you a solid runtime base that's bigger. The guys who implement the JVM have a piece of work to do to port it. So, but and then they're in C code. So if AA is intended to let you do things you can do in C, I need to have a way to say, yeah, I'm going to break through the unsafe layer. That has to happen. I don't want to do it, but Rust is doing that too. Fine. Do I want to be high level? Yes, still. So there's an escape hatch. You have to say, please, sir, I want to escape the escape hatch. Now, on multi-core, multi-threading, I want the escape on that to be pretty cheap. But I want the safety to remain. Can't break the runtime model, but you can do all kinds of cool concurrency shit, including implement Cameron's XDC model. I think that should be doable with AA. That gives you, this is what I heard Dimindu saying. Give me concurrency where it's all hidden away safe. Go routines and XDC both have very similar models.
Yeah, and I was also coming from the angle that what would I wish for in a language, given that I've already got Java and I've got all these other languages, right? Obviously, there's no point replicating what Java has, because what's the point? Because then you might as well use Java, right?
Right.
So that's the thing, that if I had the ability
like
to
my
write a new
tertiary
language, create a new language, what
Yep.
would I wish for in it?
Yes.
It has to be something different from what other languages do.
Okay.
Otherwise, there's no point.
Right. One of the things I'm doing is I'm much tertiary than Java. One of the things I'm doing is I have type inferencing. One of the things I'm doing is I have full-time first-class functions, unlike Java, who has lambdas, which are not first-class functions.
Yeah. And but those things aren't new either, in the sense
They're
that
not.
Lisp has them, Scheme has them,
That's
and
correct.
a bunch of other languages
Right.
have them.
And unlike Scheme, I'm strongly typed, and Lisp, I'm strongly typed. And my intention is that I can boil it down to C-like code for C-like performance. If you write C-like code, you'll get C-like performance. So there is there is something different there in that sense. First-class functions when you want them, C-like performance when you want it.
Yeah, speaking of performance, what's the cost of volatile, like doing that thing with the memory fence, because now I'm always have to go to main memory every time. It's
No,
like,
no.
Well, if it's a volatile read,
No.
how'd that work?
So at Java volatile or C volatile. So let's do Java volatiles, because I think you said happens before, or order it. Java volatile says, I'm just going to repeat myself here, but then I'll go implications, right? It says all the writes that happened before will be visible at the other processor. If you wrote it and he read it, the reads before will be read after. Okay. Nowhere in there did I say main memory. These guys can do cache-to-cache transfers, and they typically will. So the only thing ordering going on here is that we got a shared L2 or L3. I'm writing my L1. At the time I did my store, that's volatile. Something happened between the language runtime and the hardware, such that when the next guy reads that same cache line I just wrote, well, immediately the hardware is going to swap the cache line from one CPU to the next. It has to swap the other cache lines as well. However, that's done by the hardware. That's its hardware's problem.
Mm-hmm.
On an x86, they'll handshake at the hardware without any further instructions. If you're on a weaker memory model, like an Itanium, a Spark, a Zool, an ARM chip, you'll probably put a fence in. And that fence will say, everything that's in my cache now went from private cache to shared mutable for other guys. And when the next guy reads, he will be forced to go get from me instead of secretly reading the stale version that he's got in his cache.
Yeah.
But I didn't have to wait until I wrote out to memory. And he didn't have to wait till he read from memory, unless that's how we're sharing.
Okay.
There are some shared memory models where you're sharing through main memory, but those are pretty rare these days.
Okay. Cool. All right.
Yeah.
But your hardware has the right to make that as expensive as, like,
yeah,
you could be an H2O and do network traffic because you said volatile.
Yeah, exactly. H2O does a Java memory model on a shared distributed hash table. You betcha. And if you pick the wrong key, the wrong address to go read or write from, memory traffic. You got it. Socket open, socket closed. Actually, we kept the sockets open, but yeah. You wrote some bytes into a byte buffer. You waited. Some guy read the bytes from the byte buffer. Strongly ordered. The model's easy enough to work with and understand. I could teach systems engineers how the Java memory model works pretty straightforwardly. It wasn't hard to deal with. Most of the cloud-based memory models that people see are lazy consistency, much harder to work with. H2O's model is exact Java memory model, consistent semantics, and also they are typically fast. That's the key difference. The fastest is if you broadcast one to everybody, it's at memory bandwidth speeds. If you are pipelining from one guy to another, memory bandwidth speeds, not latency. And there's a couple other modes we did where it's bulk this or bulk that, all memory bandwidth on the network as opposed to network bandwidth. You got latency only if you ping pong back and forth. I wrote, you read, you wrote, I read, I wrote, then you take latency. Everywhere else, you got a streaming bandwidth effect out of it, which meant that for bulk big data, it was all whatever your network bandwidth is, which is typically pretty big. You're done. And we didn't do much of the big memory bandwidth except for setting up a big data set. Maybe after it was in memory, it was distributed and people did their math on their own little core section, and then they handshake, roll up results.
I will say, when we were talking about the reasons why you would split your work onto multiple nodes,
Yeah.
you covered that it could be coming at you too fast or be too big.
Yeah.
And you covered that you might do it for durability and uptime so you don't lose things. There's a third that people will replicate across multiple systems because they're mutually distrusting. And they want to have some kind of like Byzantine tolerant problem where it's like,
yeah, fair enough.
And that's where you tend to see these replicated state machines of like 3 different banks are each running all of the transactions themselves and making sure they agree on what happened.
Yeah, you're right. Yeah, mutually distrustful.
But yeah, those are the only 3 things I can think of.
Also all
why you end up in a replicated world is mutual distrust,
blockchain, and
want more availability and reliability, or it doesn't fit.
Yep. Yeah, H2O also scaled for more core counts, more CPU, GPU horsepower. That was another common thing. We split for the data set size, but sometimes we split big cluster because we needed more CPUs. But that kind of goes in a resource scale limit. I think you're right, because Byzantine's a good one. Total hard uptime is a good one. And then resource scaling is a good one. Well, here we are. It's noonish. I don't know what I ranted on, but I think the language design, we could get more specific on language design. I have a bunch of language design things I'd love to go talk to people about that I'm sort of sweating bullets on right now. And you're like, no, it's going to be hard to do this, but that's not actually my problem right now.
Sure.
Next week, we can get back to syntax. We managed to go an entire week without putting a line of code in the doc.
I like the syntax hacks because it's kind of everyone can like pile in, like it's a low bar to jump over, but it's still entertaining to think about.
I had a very specific topic I wanted to go into today, but unfortunately we've run out of time, I think.
Tell us now.
Which is to do with how to implement, say, constant propagation in my compiler. So I don't know if we have time, but can I scribble something and?
You can go quick on it. First thing I'll tell you is your IR sucks, and then constant propagation is hard. Which IR is easy. Then you're like, oh.
So I've been reading up on data flow analysis and
global value numbering,
and so on.
One answer, GVN.
Yeah, right.
Okay. Well, can I scribble in?
Yeah.
In this Word doc?
Yeah, that's the point.
Okay.
There's that code section down below, or just
maybe code section down below.
Just whack some blank lines in.
So here's what I'm just gonna scribble something so that
yeah.
So I'm just writing here some what may look
Matt,
like
can you
Lua
drag
code.
Up while he's typing, can you drag up sea of nodes and maybe the GVN paper, the global value numbering paper?
Oops. This how do I turn this off? Like it's trying to. reformat.
Okay, we have amazing tech support. You write something you're hoping that looks like some code you're trying to write. Somebody comes behind you and turns it into a Roboto mono font, does syntax
Yes.
highlighting and shit like that. It's kind of amazing.
Yes.
Doesn't
Okay.
always work.
Anyway,
but
doesn't matter.
yeah, it
I'll
doesn't matter.
ignore that. So let's say this is just some Lua code, right?
Right.
So I've got here a variable, right?
And you're trying to tell me
And
that
I've
the
got,
first, the auto capitalization is annoying. And I agree and I live with it and carry on.
so I've got a function here, right?
Happening already.
And where I'm
You
accessing,
remember doing this.
so where I'm let's say I'm saying return 1 plus X, okay? It's a very simple function,
Yep.
right? And I've got another function, which is say bar and oops, I don't know what it did there.
Don't worry, carry on.
And sorry, tabbing is creating something. It's a
Yeah,
table,
don't
is it?
do tabbing, use spaces to, or fixed size font, so just do some spaces. It's all
So
good.
let's say I've got another function here, and that's saying something simple like return 2 plus X, right?
Yeah.
So my problem here is that I want to be able to detect that this is a constant, right?
Yeah.
Now in Lua world, what this is, so in Lua, all functions are, so when you access something like this,
Yeah.
X, so here X is local to this whole code, right?
Okay.
To this chunk. It's
Yeah.
called a chunk in Lua, right?
Okay.
And when you refer to this X here, it becomes what is called an up value. Up value means
Yep.
that
I understand.
it's referring to something which is on the stack of the parent.
Yep. Yeah, you're outside the scope. I get
right?
it. Yep.
Oops. What
Somebody
happened
deleted
there?
too much stuff because you had auto selected and there's too many people there. It came back.
Okay. Do I still have stuff or is it gone?
Oh, I see stuff on the screen.
Okay.
I see
All
local
right.
X equals 1 as your
All
chunk,
right.
function food,
Yeah,
function
yeah.
bar.
So when I'm parsing this,
Someone should be sharing the screen so that we can see it on the.
Oh, I can do this. I'll do this now. Carry on.
Always forget about the
Keep talking.
YouTube people.
so yeah, so I'm just so when I'm parsing this code, I recognize that X is an up value, right? And it's in the symbol table is flagged as an up value, which means that it refers to something which is in the parent scope, right? And so in my syntax analysis during the phase I'm building the AST, I recognize it's an up value. And by definition, up value means that it's escaped in the sense that somebody else has got reference to this up value, right?
Right.
But what I want to be able to figure out is that these functions, even though they're accessing this up value, they are not modifying it in any way.
Yep.
So therefore, this is a constant.
Yep.
And therefore, I should be able to replace this by 1 and this by 1, right?
Yep.
And so in the final,
right.
Yeah, that's what I want to achieve. Now, my question was really,
how do I do it?
I'm already flagging this as an up value at the time of parsing this into AST, right?
And put your X's back in your functions. You got them still at ones. But I understand the problem. I understand the solution. The solution here is that you have to go as part of your, I do this as part of my R. You have to do somewhere in your analyses to declare that you have found all the writers of the local X.
Right.
And that foo and bar are being called only after all the writing is done. So an easier answer, say, I found all the writers. There are no writers. Because there are no writers, it's a constant.
Right.
Now, constant propagate as you expect.
Right.
But if you have writers and you think it should still eventually be a constant, then you need to say, at some point I am done writing. And furthermore, I can prove that I am done writing. And now I'll take whatever that value is. That's my constant for foo and bar.
Right. I'm trying to do something not. So if it's a write, if there's any writer, I treat it like a non-constant, right? So it's an even simpler model. I just want to be able to identify constants which are never being written to, and therefore I can optimize the code and I can say, look, even though it's an up value, it's actually a constant, and I don't need to worry about it.
We'll put your X back so you can see the problem here a little bit.
Yeah.
Okay. This is a two-pass.
So that's what
two-pass problem. Make a pass. Go find things that no one's writing to. There's your
Right.
constants.
Right.
Okay, flag them all as constants in your IR. Whatever your IR looks like, somewhere you reserve a bit saying, and there ain't no writers.
Right.
And now run your other constant propagation sort of straightforwardly from there.
Okay.
When I do
And-
this in AA and see the
Mhm.
nodes IR, all memory-like effects have loads and store nodes in a graph.
Yeah.
And functions that refer to somebody up level goes to a frame up to go get
Yeah.
something. But at that
Yeah.
point, I can totally do, the last writer's done and a constant value was written, and this function is only ever reading from that point. All is
Right.
IR node. I'm filling edges in a graph. It's all straightforward graph semantics. If you got an AST, you'll have something similar. You'll walk up the tree in the AST, you'll discover I got a local here, I find all the writers, there's a flag on here that I've summarized the writing somehow. In the graph, I summarize the writing by the structure of the graph itself. In an AST, I might summarize the writers by putting a flag on the local X, and ain't no writers below here.
Right. So my question was really also, at what point should I do this? Like, I create AST and then I have an IR as well. So I generate the IR from this, and then I have the IR to C translator, right?
Yeah.
So should I do this
Okay.
at the IR level?
Typically, you would do this at whatever you're calling an IR, and I don't know what your IR looks like. An AST is already an IR. You have another IR besides the AST. You can do this on an AST. You can do this on some other IR, and then it's and the C compiler will do this itself also when you translate to C, as long as the translation step isn't too obfuscatory, which it might be here. C compilers don't necessarily do well with upscope behaviors. So if you have an IR that is intended to support optimization, I claim that IR should do the optimization, right? Well, what's your next layer IR?
Yeah, I mean, I wish I could show you that, but maybe I can, but I need to.
So I'm going to claim this is not a short question anymore.
Yes.
About the structure of IRs. So the point of an IR is to let you easily do transformations to optimize code, such as constant propagation. That's the point.
Right.
So if you have an AST, which I claim an AST is a different point to it. An AST's point is to be an easy first step coming out of syntax.
Yeah.
It is often also the case that you can do a lot of optimization fairly easily on an AST.
Right.
So unless you have more optimization that an AST easily supports, I wouldn't bother with another IR level. If you have to do some major translation step for which a rewritten AST is no good because the Lua to C translation is difficult to do, maybe you need another IR. And maybe you're going to LLVM IR, for instance. If you're going to LLVM IR, LLVM will do it. What the hell? Just let it go.
Yeah. But in Lua, all variables are stored in the heap in this. Anyway, I mean, maybe I need to explain why I can't just leave it to the C backend.
You're doing a lifting transformation where you're trying to get something out of a C struct or a heap struct into, for instance, a stack-like behavior, so the C compiler can do something reasonable.
Exactly.
Yeah. Okay. Yeah. So if that transformation does not fit well in an AST, then maybe another different AST makes sense. A different model, it's not an AST, makes sense. I claim that you could do a lot of that on an AST.
Sure.
And you just live with an AST. If you're going to change from an AST, I would go to my graph model, and then you get it out of your graph model too. But then you're doing the things that LLVM does, which
Okay.
If your goal is to lift and let somebody else jit the code, lift and leave all the fucking constant opportunities around, because the guy who sees it after you've lifted it, in theory, knock on plastic, will totally constant fold for you.
Exactly, but I need to make it visible to the
you have to lift it.
C code so that the C code doesn't get fooled by the fact that actually
you have to lift it enough the C code sees a reference to some stack local variable X, not a heap reference to some struct, the heap struct thing that's got an X field.
Yeah.
So I claim that you could still do this as an AST, but I don't know. And I wouldn't bother to do the constant folding directly yourself unless you can't express it in C. So here's a counterexample. The guy's doing like Charlie Gracie's not here, like Dython and JRuby and the like have different call semantics where it's difficult to express them in Java bytecodes. the direct way. So they spend a lot of scheme too, has a lot of effort put in to figuring out what the call targets are, but then they can't even express the call target easily to the JVM. So they fucking write, they go to an IR where internally they can discover a call target, and then when they transliterate it to JVM bytecodes, they give you the call target as essentially a constant folding of a function call, not of the number one, but a function pointer, because they have to express it so directly because the JVM doesn't understand the call sequence. You may not be in that zone yet, and if you're not, I would skip that. I would say, I'm an AST here. I'm going to change it to a new AST that's same as the old AST, except I rewrote the local guide to be a stack allocation marked, and then when I pretty printed a C code, it pretty prints as a local variable in the C stack with the number one.
Yeah, it's just that at the IR level, it's easier to know what's being written to, right? Because in the IR, you have explicit stores and loads, right? So therefore, that's the reason. Whereas in the AST, I can't easily see unless I analyze this.
I say you're going to do the analyzing one or the other. If you need to go to the direct memory model, I would go to CF nodes. Take, eat that with a grain of salt, because I've enjoyed this thing for 40 years. Not everyone does. Do what you need to do. As soon as you go to another IR layer that's got more direct def use chains and more allocation load store behaviors, still the propagating of the one is not exciting, because the next layer down will totally do it. Instead, the propagation of things that the next layer down won't do is exciting, like figuring out the loads and stores are stack-like, and I want to put them on a fucking stack and make them a stack instead of making them a heap allocation. That's exciting. Don't repeat what the next guy does if you can avoid it, because you won't get any gain out of it.
Yeah, okay.
Right? You'll never see any performance work out of that. No performance comes out of replacing that X with a 1. Performance comes out of not allocating the local frame that holds an X and loading the X, which is a 1, and writing the return value as a back into some other frame thing. Like, get your gains where you're going to get your gains, and let the next guy do what he's going to do. And he's going to do +1. That'll be fine. But he won't, as you say, he's not going to tease apart your memory model.
Yeah. Okay.
All right.
Thanks.
This is a longer discussion, and I don't want to go forever. So we're already well over 2 hours. So I'm going to declare a victory. And say, bring it up next week. We can totally go down this path again next week and say, what is the IR that you need to discover what you need to discover? And does it make sense to have it as a more of a graph thing, or more of a classical control flow graph with basic blocks? Or do you want to have just an AST again? And you can do it with it. I claim you could probably do what you're trying to do with an AST. That might be the easiest way to go. I don't know. All right. For me to get.
Took me a while to find the screen here. Anyway, goodbye.
Yeah.
Just want to say goodbye.
Happy New Year, everyone.
Happy New Year. Yeah.
Yeah. Happy New Year.
Happy New Year.